I would invite Dr. Rajesh Kumar from Adverb Technologies. Then Chirag Jain from Endure Air. 2 minutes, okay. Popov, please take your seat on the dais. Lalit ji from Center of Excellence, Kavach. Anushri Verma, Senior Director Analyst, Gartner. I think we can start the session. Yeah, you can sit here. Madam Maithili Kamath, Senior Director Electronic Solutions, Aerospace, Honeywell. And what is his name? Please come down. Come up. George? Korean. George Koil Pillai. Yeah, George Koil Pillai from Honeywell as well. Chirag, welcome. Nagaraju from Center of Excellence, Kavach. Ma'am, can we start with yours first? Ready? Yeah. So we will start first with Maithili Belli Kamath, Senior Director, Electronic Solutions, Aerospace, Honeywell. Before we start with the presentation, I would like to give a brief about her academic and professional background. Mrs. Maithili, she brings over 22 years in avionics, spanning software systems, verification and validation. She leads engineering transformation for advanced flight controls and FMS, platforms, hardware and software team. She mentors Honeywell India's women employee network and is dedicated to mentoring and transformational leadership. Ma'am is working as the Senior Director, Electronic Solutions, Aerospace, Honeywell, has been for 21 years in Honeywell itself. And we are fortunate to have you here today, ma'am. She'll be highlighting the aviation's shift from automation to autonomy, where responsibility moves from pilots to intelligent systems, using the 4-pillar autonomy mindset of see, think, and act, and communicate to enable safe, more efficient, and autonomous free flight operations for the future. I would like to invite Ma'am Maithili and her colleague, Mr. Kovil Pillai, also to make the presentation.
All right. First of all, thank you for such a warm introduction, MD sir. And truly, it's been an honor and privilege to be standing in front of the transformational workforce of CRIS, who are here to bring a revolution in the way the mobility sector is going to happen. And the proof lies in the pudding. We are seeing right in the beginning of the day, right from the ministers to MD sir himself, talking about the actions that are already in place to bring this transformation, and the thoughtful leadership to invite industry peers to come and share their perspectives on what the future of mobility is itself is a right step in the making. Throughout the day, I think around 2 hours or so, sir, I could see several parallels that are there in the sectors. I come from aerospace, and I already have found so many areas of collaboration that Honeywell and CRIS can partner with. So without much further ado, so today's agenda, it's very simple. I'll just give a brief of Honeywell, why autonomy is needed, and then automation and autonomy. What is the roadmap and what are the 4 pillars of autonomy mindset. And my colleague George is going to actually talk about each of those pillars, how we are doing the work in aerospace, and how it is having a very good point of view in the railway sector as well. So that way we can connect the dots and we can learn from each other. So I started off my career with Honeywell. I'm the first woman engineer in my family, with a very humble background, and very fortunate to be working with Honeywell, a Fortune 500 company with more than a lakh employees, around 42 plus countries. Um, we are so proud that our business caters to aviation, automation, and energy, and align with these 3 businesses, we have connectivity, because connectivity is a core in the offering that we provide. And India commitment, it's just not the other day that Honeywell has been there in India. It's nearing a century. Our first association with India was in 1930s, where the technology to license in Digboy oil refinery was being established. From there to now 100 smart cities, and then moving on to aerospace, aviation, the number of capabilities are unlimited. And so proud to say that our Honeywell in India is entering the $1 billion revenue club in 2025. So it's really a very humbling, a very proud moment for me to stand over here and share the insights of one particular vertical that is going to be on autonomy. So at India, we are also the core of the technology workforce. Controls, autonomy, digital transformation, and energy transition are some of the key technology areas that we feel very proud to be making a change. So let's dive directly into the topic. Why autonomy in aerospace? As we all have seen over the years, there has been a lot of transformation starting from automation, but the need for autonomy comes from 4 pillars. One is, we have seen post COVID, the amount of air traffic has increased by 30%. So much so that IATA is predicting that in the next decade, there will be 30 to 40% of pilot shortage in the industry. We are also seeing 2 key insights. We are also seeing safety and reliability are also contributing to some of the critical accidents and incidents in the aerospace sector. What does it mean? There's a lot of human in loop and lot of opportunity to make smart machines smarter, think and act as well. So it is not something aspirational, it is not something as a nice thing to have, it is the need of the hour. And aviation autonomy is now. Why do I say that? As we speak, Honeywell is already doing joint technology development with several of original equipment manufacturers, as OEMs, as what we say. As latest as last week, we did an autonomous mission demonstration in the Augusta Westland 139 demonstrator, wherein we took off and then enabled a helicopter to hover frontways. All that being possible with the collaboration with the near Earth autonomy. So these are few examples where I want to emphasize that autonomy is a fulcrum. It is a core in how aerospace is going to function. Now, we all have seen a lot of technological deployment has happened in every industry sector. We talked about how the ticketing system is being automized. We talked about how predictive maintenance is being put in place. We also talked about how safety is being taken care of. But what we need to make sure that we all understand is, what is the major difference between automation and autonomy? So when we talk about automation, there are 3 distinct factors that come into place. What are they? They are human in loop, decision making, and operations. So when we talk about operations which are routinely being conducted, right from then the pilot takes off from an origin to landing to a destination, there is where the automation comes into picture. But when we talk about autonomy, it is about how we equip the systems to see, to think, to act, and to communicate. So if we are able to address these three pillars, which is on decision making, human involvement, and scope of operations, then we are setting our path to autonomy from automation. Now, how does this look like? Is this something, again, a wishful thinking? Let me take you all to the 1980s. In the 1980s, can you all take a guess of how many members were there in a cockpit to man a mission? There used to be at least 4 members in a cockpit: a pilot, a co pilot, a flight instrumentation engineer, and a navigation engineer. Because of certain automation systems like flight management systems, like automated flight control systems, we were able to bring that automation that required only 2 people to be in the cockpit to man a mission, which is a pilot and a co-pilot. So what does a flight management system do? It actually prepares a flight plan, it actually does the performance prediction, makes sure that the aircraft is navigating from an origin to a destination, of course, keeping the performance prediction and the safety of a passenger intact. All this is being done by keeping a human in loop. Now, if you look at the current state, we are talking about reduced crew operation. So, what does reduced crew operation mean? Let me take you to 2023, where Honeywell collaborated with Airbus up next and did a reduced crew operation demonstrator. So, what does this mean? In case of a contingency event, in case of a pilot incapacitation, the system is able to identify which is the nearest and safest destination and land the aircraft there. So this is a joint technology demonstration that Honeywell did with Airbus. And then moving on, we are talking about single pilot operation. What does that mean? We are talking about a virtual co-pilot in the crew, but able to give the insights and the decision-making capability to the system on board. And then at the end of it, the penultimate, we are talking about autonomous. So from 4 to 2 to a digital twin, and then moving on to a uncrewed aircraft. So all this is not done just by organizations like Honeywell, but also we are working with regulatory bodies, because as you all know, it is the lives at stake. It is about making sure that the safety and reliability are intact, and it is also to equip the system which can take decisions in a fraction of a second. Because even now, if you look, even 30 seconds is not enough for a pilot to take a decision at present. So the need of the hour is, how do you make systems smarter, safer, resilient? And that is where the power of AI, the power of ML, the power of sensor fusion, the power of connectivity comes into picture. So far, we all learned about why autonomy, what is the difference between automation and autonomy, what constitutes the path to a fully autonomous sector in aerospace. Now, talking about mindset, because the theme for today's event is about from perception to action, the future of mobility. For that, we need to make sure that our base is very intact in terms of traversing ourselves to what it means when we say autonomy, and what does it mean when we talk about autonomy mindset. So there are 4 pillars. What are they? One is sensing, that is perception, right? And second one, we are talking about thinking, the act of decision making. Then we are talking about control, or where we have the human machine interface coming into picture. So see, think, act, and communicate. So when we talk about autonomy, there are a lot of sensors on the aircraft, and you all can stay tuned for next couple of minutes where George will come and talk about what are the parallels when we have it in our railway sector as well. When we talk about C, it's just not about what is the input and output I'm getting into. It is about knowing which are all the available sensors in an aircraft that I can fuse in order to make meaningful decisions. Second, when we talk about think or decision making, how do I actually allow the machine to understand where it needs to act? At the end of the day, it is about, in a particular commercial aircraft segment, it is about making those interpretations when I'm having a weather turbulence, when I'm having a undue traverse of the aircraft path. How do I make sure that my bias from the required navigation path to my current path is being taken into care accordingly? And that is where the power of AI and ML comes. It's just not that it's a cool thing to have. Most importantly, we have to act. The principle of aerospace is very simple: roll, pitch, yaw. How do I make sure that these commands are getting into the actuators, the control surfaces, so that my aircraft can maneuver and reach its path? And most importantly, it is also about creating the ecosystem where I communicate. So what do we mean by communicate over here? It's just not about having a satellite communication and having couple of LRUs talking to each other. It is about the entire aircraft able to communicate to other aircrafts which are there in flying, as well as the ground station. So that means my ATC controller also has to be smart. It has to be equipped with the know-how. So that is what I would say about the four pillars of autonomy. And with that, I would like to invite my colleague George to go into these pillars in detail and draw parallels towards the railway sector as well. So over to you, George.
I think before George comes in, let me just give an introduction about George. George Kovilpillai is the chief engineer in the aero business unit of Honeywell and as the design authority for all aerospace electronic product and system software verification and validation. Prior to joining Honeywell, George was a scientist in Aeronautical Development Agency and had the responsibilities to define and validate the integrated avionics function for light combat aircraft. It also served in Hindustan Aeronautics Limited in the areas of navigation and attack systems and precision navigation sensors. George holds a bachelor's with honors in electronics and communication engineering and a master's degree in engineering from IIT Chennai. He is an INCOSC certified expert systems engineering professional. He specialized in the field of aircraft navigation and guidance systems and led the development of aircraft landing guidance function for many aircraft programs. He led a team of systems engineers at Honeywell to install Honeywell's GPS-based landing systems at Chennai Airport. George was involved in customization and integration of Honeywell's inertial navigation system Talon on the Pinaka and the Akash launchers, as well as on the advanced towed artillery gun systems. May I call on George, please?
Yeah, I'll try to be faster to stick to the time. Yeah, so straight away to the topic. When we say see, it is mostly about situation awareness, right? You want to be aware of your situation around. So if you take just a simple example, 10 years before, or no, maybe I would take my own example, maybe 25 years before when I started learning to drive car, the sensors that I today have were not there. I might have made many accidents while parking and taking out the car itself, right? Today, if you drive in the US, see, every car comes out with a blind spot monitor, a lane assist, or a pedestrian monitor. The situation awareness, as it increases, driving becomes so easy, right? So even a car on the road. So in the US, earlier we used to take a map and then study, plan very well. Today we just put a GPS, no navigator, and then drive through. So the situation awareness is very very important for any kind of transportation. It is more so for safety critical applications, something like when it comes to aircraft or trains, the large number of people travel and any no accident could be very fatal, right? So when it comes to safety or situation awareness in aircraft world, we are talking about multiple functions. The first one could be awareness of the aircraft position and the orientation. That's the first thing. Now, second thing, if I have to add some more, the weather information, that is very critical. So as the aircraft flies, you need to know the weather conditions maybe hundreds of kilometers ahead, so you can plan your flight plan and fly the right route. Recently we read uh, news that's one of our aircraft while flying to Kashmir had to avoid weather, but because the other, no, we could not get clearance from the other ATC, it had to go through the, no, weather. That's a very important decision making. If you go through the right through the eye of the bad weather, the aircraft may have crashed. But you have to make a decision that how much I deviate, still come out with a broken nose, right? We all might have seen that now aircraft. So similarly, so if I go to the one more, the air traffic on the road. Now we all in Bangalore, we all put, no, even if I have to drive 2 kilometers, my house is in on the same campus where my office is located. So when I take my car, first thing I put a map and then see how is the traffic, because sometimes it's so congested that I cannot even, no, just 2 kilometers I would take half an hour or 1 hour. So I just walk down, right? So the situation of the traffic is very important. In here, it is even more important, right? So if you just browse Google, now the traffic collision avoidance system, averted accident. In India itself, I just did a browsing just before coming here. I saw some four no, incidents. Some of the international flight flying through Mumbai, no, Air France and Qatar Airways just avoided collision because of TCAS. And another one I saw, the Indigo flights. Now, so one was taking off, one was coming down. They avoided, the collision because of the TCAS. The situation awareness of the traffic around is very important. So I can go on adding. Another one is the terrain awareness, right? As the aircraft flies, you need to be know which is the highest point in that place. So the host of technologies that provide no situation awareness. When I sometimes I feel that if only my car has got surround cameras and my dashboard becomes the complete situation awareness, is like how easy it would be for me to drive, right? It would be very easy. That is what is required for a pilot to fly. But just think, now, so when we talk about these kind of systems, the probability of an accident, now it has to be very less, because the probability, the conditional probability of fatality if there is an accident happening in air, or if there's something goes wrong in air, is very high. So you need to avoid such things. So the systems has to be very reliable. When I say, if the probability of misleading information is 10 power minus 6, the pilot comes in and then increases that probability to very high, or I would say reduces the probability very low. It becomes minus 10 power minus 9. If you take that pilot out and make that aircraft to fly autonomous, so your system has to be much more reliable. So I just took one example here. Situation awareness, I'm talking about the position of the, I would call it that vehicle. It could be aircraft or it could be train. Really speaking, aircraft, in aircraft world and train, the kind of probabilities we are talking about, safety related probability are talking about, is pretty much same. In fact, there are articles that say these were derived from the safety numbers that were worked out for trains, because trains carry thousands of people. So even in one accident, there could be very high number of fatality. So we are talking about the accuracy, availability, integrity of that information that is available to the pilot, or if there is no pilot, to the vehicle, so it can manage very well. So we are talking about accuracy of in aircraft. We are talking about 10 nautical miles all the way down to zero point 0.1 nautical miles. So if I take the 10 nautical mile, when an aircraft flies from, let's say, from US to Europe, the Atlantic, so almost 9-10 hours, the aircraft just flies with no land aids. All that you have is the GPS. In a bad day, if the GPS does not work, the aircrafts are thousands of aircrafts are flying across. So they would be just flying blind. There is no nav aids. So the secondary navigation system is the inertial navigation system that drifts almost 2 kilometers in an hour. So 1 nautical mile is what we say. 10 hours you would have drifted almost 20 kilometers, right? So another aircraft in the next track also would have drifted 20 kilometers. So we place the aircraft almost one latitude apart, almost 100 kilometers apart. So when we take advantage of the winds that are now always there from on the poles, so aircraft can consume less fuel and then fly faster. We are not able to bring the aircraft closer because you need to take care of safety. So in all these cases, whether train or aircraft, safety takes precedence over speed, right? So it has to be very, very critical. So and even more important is the availability of the function. So we say 1 in a million can be the function can go can be not available. So even more critical is misleading hazardous misleading information. If the sensor gives a wrong data, everything goes wrong, right? So the aircraft gets into the other aircraft path. So we say 1 in a billion. So all these probabilities, to achieve these probabilities, so you have sensors that has to be reliably working, and you just take the pilot out of loop, then no, it becomes even more critical. Say pilot can at least have some sense, and then maybe take care of the situation when the sensors behave bad. So we are talking about, with all the GPS jamming, GPS spoofing, all kinds of GPS related difficulties, we are talking about integrating large number of sensors. So Honeywell is working on very non-conventional technologies. For example, tracking the star, it used to be in the space. Well, we launch the CRAPS. So celestial navigation, radar navigation, magnetic navigation, host of other sensors, we can fuse all of them to make a very good sensing navigation capability. So go to the next slide. Yeah. Yeah. So same is true for train as well. You need to have a highly reliable navigation. If you have to take the driver out of the train, if you have to move the train faster, so we need to leverage all the sensors that are available in the railway network to augment and maybe create a very good navigation system that can augment GPS and then existing navigation system. If we have to take or move trains faster, autonomous, then you need to have a highly reliable sensor on which we can depend upon. So the aircraft and railways almost pretty much fall on the same category. So coming to thinking, at various stages, we have decision to make. The data is available. We have to make decision. As I said, also the recent example I took, while circumventing the weather, because the other ATC could not give clearance, the aircraft has to fly through the weather. But if it had flown through the eye of the weather, or if there is a bad weather behind the existing bad weather that is known, it's going to be dangerous. So a lot of thinking has to be done, right? Many accidents happen at the I'll just take another few minutes and then yeah. So many accidents happen closer to the runway and the takeoff and landing, right? So if I take the mid-air collision, pretty much it is no more we hear about mid-air collision. But recently one happened in the US, when aircraft was coming to land and helicopter got in the path. So even today it happens, but it's very rare. But the TICA system has become very reliable. The sensing and avoiding is a technology that has to mature and has to be very reliable to make the trains and aircrafts autonomous. Coming to the close to the ground, so mid-air has become pretty much mature, but still we have a lot of incidents we hear on the taxiway, right? Recently we heard one aircraft was coming to land, and then he saw there is another aircraft on the runway, so he just touched down and then went around. You know, at least two incidents very recently happened. So another one, the an aircraft was just crossing um, the runway when another aircraft was coming to land. So these are all situation awareness. So if you with pilot there, he could notice that and then no went around. You just take pilot out, then the system has to be super intelligent to replace the pilot, right? That's the important thing we are talking about, the thinking. The pilot's thought process has to be implemented into the system. We are talking about AI. So many a times if you ask the student, what is the accuracy you got from your prediction, it's a 90%, 95%. You would say that's not suitable for your application, because it has to be 99.999, I say 59 no, probability. So it has to become very, very reliable. Then only you can put it to systems like aircraft and train. So because of the safety criticality, the system has to be very reliable. So there are a lot of opportunities where we can think of thinking capability into the aircraft, the weather, traffic, landing, takeoff, and even on the parking. So if you just browse, there was an aircraft, a large aircraft, one of the largest aircraft. Now it was parking in a recently parking in an airport, and then the middle of the wing went and hit a lamppost that was there in the. I was just wondering, what is the situation of? Still, we have to improve. Now, if it touches the wingtip, it's fine. The middle of the wing touching on a pole that is permanently there. So the situation awareness has to improve. There are a lot of opportunities to think. Just think of the Mangalore accident. The pilot was coming to land, so he was way above the landing path. So it's a fraction of second decision whether to go around or make a decision to land. So he took a decision to land. So he landed in the middle of the runway, and next he should have continued to brake. It's a fraction of second whether I will be able to stop. It's better to stop or better to go around. So he decided to go around. He could neither take off or stop the airplane. So these are fractions, a lot of thinking that runs into pilot's mind. Pilot avoids a lot of accidents. If pilot has to be taken out, the systems have to be very, very reliable. So in trains, same thing happens. I just put a concept picture. So easiest or safest way is to stop that slow moving train at loop A. Now, if you have to allow it to go to loop B to move it faster, now you need to know doubly sure that the fast train will not now come to loop B before the slow train reaches loop A. It's a lot of information has to be shared, thought through, decision has to be made. So without now sacrificing the safety of the passengers and the train, right? That's why that now thinking is very, very important. So coming to the autonomy, the last couple of slides. So that I talked about many of them, the landings. So Mangalore example I took. It's all once the pilot is not there, the systems have to collaborate. They have to share information. They have to sense and avoid. They have to collaborate each other and then fly together, land very safely. So there are a lot of areas where the final control has to be applied. So with the data has to be reliably shared. So if you take communication, that has to be super reliable, right? So now that if an aircraft is coming to land, let's say in a Cat 3B, the aircraft or Cat 3A, the aircraft has been brought down to a level of 50 feet. Now, there the cloud ceiling, he comes out of the cloud ceiling. If the aircraft is not on the right path, at least at the 50 feet, pilot can make an eye contact and then make a decision, right, to go around. But now if the pilot is not there, now the system has to do that job. Whether I'm on the right path, whether I'll be land at the right place, or I have to go around. So there are a lot of such important decision making has to be done. Similarly, I put a concept diagram for railways. So you have to augment, make the communication robust. At no point in time we should not be left with no communication. There was one incident I think happened in one of our airport. For 20 minutes, all the communication system, radar system, everything failed. By God's grace, no accident happened. There were few tens of aircrafts on that vicinity. In that, so everybody somehow collaborated and then averted the failure. Just think if the pilot was not there, it is very, very super critical. I've read about Kavach, I've read about railway system. I was very impressed. It is fail safe. The safety was prioritized over speed and other aspect. The beautiful systems. If only we bring little more technology, augment three, I put 3 layers of communication here, so the train can be reliably moved autonomously. And so it's a concept, maybe soon we'll get to that. So I would request Maithili to come and now maybe talk the summary slide. Yeah, okay, fine. Thank you so much.
Yeah, thanks, George. I think that was a wonderful presentation. Sense, think, act, and control. If any of you can have any questions, I think we can take them now, or if you can reserve it towards the end, we can club all the speakers and take them. One or two questions, quick. Yeah. If there are no questions, I think we'll now go with the speaker, Dr. Rajesh Kumar. He's the principal scientist in advanced robotics, Adverb Technologies. Dr. Rajesh is a robotics PhD from IIT Delhi, led R&D at Adverb Technologies and developing advanced robotic systems, legged robots, quadrupeds, humanoids, collaborative arms, exoskeletons, and haptic devices. Skilled in software and intelligence module design, he has published around 30 plus papers, filed 12 plus patents, and mentors at leading technical institutions across India. He will be highlighting the challenges that scaling, locomotion, and manipulation in robotics and AI will face. He will also explore how technologies can overlap to benefit both railway automation and advanced robotics. Dr. Rajesh.
Yeah. So good morning, everyone. Thanks a lot for the nice introduction. So it's like I'll just explain a little bit about Adverb, and then how robotics is evolving across the globe and in India. So we are not railway people. We know very little about railways and how mobility works. We understand robotics. So the idea is I'll focus on how robotics, how what challenges do we face in like control, perception, mobility in the context of robotics, and then maybe we can align. You guys can understand and maybe take some cues out of it and like how it can be implemented in the context of railways. So I'll just explain about Adverb. So Adverb is a robotics company. We started in 2016. Started from a small place in Noida. Now we are like a global company with offices across the globe. So we build numerous robots. So, for example, railways, a train is a machine, an aircraft is a machine. Similarly, the smaller versions of it, like a wheeled robot, a robot used to take material from one place to another. So why we call it a robot, not a machine, is like there is an implied intelligence involved. You can, the robot has to move from one place to another, has to make its own decisions. Decisions can be in terms of control, in terms of perception, in terms of locomotion. So our idea is that we tend to solve locomotion and manipulation problems at scale. So we make different platforms. We make wheeled robots, we make legged robots, we make arms uh, for different use cases. So for example, a collaborative robot, it's an arm which can like manipulate objects, pick object from somewhere, place object to another place, and do various things. So we make legged systems. Legged systems in the is like you need not for difficult terrains. Why would you have wheels? Wheels would not allow you to move into like various different terrains, and also so we tend to put legs for off-terrain locomotion. You can move around, walk around. So it can be four-legged robot, it can be a two-legged robot, it can be a wheeled robot, it can be a wheel plus legged robot. So we make all those platforms for different applications. For some for mobility, some for warehouse automation, some for defense purposes and all. And then comes the full-fledged human form of a robot, which is like a robot has arms, a robot has legs. So this currently we are not into advanced stages of actual. So this is into initial stages of development, and 2 or 3 years down the line we would have a proper functional humanoid robot. The West is doing it, so we are doing it in India as well. But right now, the major, so all these robots have different parts, right? They're like different platforms, different things of the same what you say, same low level ingrained stuff, which is like an actuator, right? The mechanical part is an actuator. You can have an harmonic gearbox, you can have a planetary gearbox, you have a motor drive. So a humanoid uses 29, a quadruped robot uses 12. So they're like, so when we talk about a robot, it's more like a combination of actuators placed into different forms to deliver a particular task. So a robotic software or a robotic principle is like you have a hardware architecture. uh, Either you have 12 actuators, you have for a quadruped, you have 6 actuators for an arm like robot, or you have a 29 or 31 actuators for a humanoid. They all have to work together. Or maybe when we say a robotic fleet, it's like multiple robots have to work together to achieve a common goal. Now the question arises, how do you do that? It's like if I say a quadruped has to walk, so there are 12 actuators. A lot of decisions have to be made. Where to place the leg, how to place the leg, what forces to apply, where to go, how does the environment look like, what does my first initial step go in the direction of completing the task. So all these questions arise. So there have been like two different paradigms. So why I'm focusing on that is maybe in the context of classical systems being developed and modern systems being developed across the globe, how the paradigm is shifting. So it's like 10 years down the line, 10 years ago, what we used to do is everything that you have to do, where to go, how to go, what to do, all these questions have to be formulated like using some differential equations. You have to formulate, okay, I have to, so you have to model the system dynamics. You have to know how much torque should be applied, how much the robot should be placed, how much force it will apply. So there are two paradigms. When we say is a classical paradigm where we model everything, everything goes into classical principle, and the latest paradigm, which is more like a trained system that you don't care. You fundamentally don't care about the fundamental knowledge of a robot. For example, we as humans, we do, if I have to walk, I don't solve a differential equation. A small kid when it's born is like trains itself to walk. So a similar paradigm, can it be applied to robots? So we and like people across the globe, they do the same thing for every kind of robot. For a wheeled robot, for a legged robot, for a humanoid robot, for an arm, is like you put it into a simulator, you put it onto the real world, you give it a task, it will try to achieve a particular solution. It will fail in simulation first, and then it slowly, so there is a neural network training itself to achieve a particular task. And as as iterations go by, it there are rewards. So there's something called as reward modeling so what I'm telling you is fundamentally called as reinforcement learning. Is like there is a robot in simulation. The robot is trying to do a particular task. It's not able to. The motors are not able to coordinate at its start. Slowly and slowly, for every failure, there is a loss. For every success, you give a particular reward. And slowly, the robot trains itself to achieve a particular task and it succeeds. So, this is one paradigm. The other paradigm, which has been in classical domains, I'm very sure, so I'm not a railway person, but I'm very sure the similar paradigms would be there in railways as well. It's like you model multi-agent coordination, you model a lot of optimization stuff, and try to figure out the best solution. The same thing we do in robotics. We model so a model predictive controller, which is being used for legged locomotion, requires a lot of optimizations. But the same thing can be also achieved by training the robots. The problem with training the robots is we don't know what's happening. But the better part is we don't need to model everything. We don't need to model weather. We don't need to model the soil phenomena in a differential equation sense. We obviously need to model in a finite element sense in the simulator. Is like that how the soil behave, how would the weather behave, and let the system evolve to generate that behavior where it can coordinate itself. So I'll focus on two major aspects in robotics, both classical and uh, the AI sort of, or physical AI as we call it, part is like in a traditional control or a traditional SLAM. So there is a fundamental problem in robotics known as simultaneous localization and mapping, where so So as in the previous presentation, sir was talking about the issues faced using GPS and all. So in railways, in trains, it's a better thing that you have a GPS based localization system. But most of like 60 to 70% robotics is indoor. So we are into GPS denied. We don't have the ability of using a GPS all the while. So we use cameras, lidars, other sensing devices, IMU sensors, and all to localize the robot where it is. It's like, so the robot has its own understanding. Okay, I would have, so if it's a wheeled robot, it has moved 5 centimeters by the wheel odometry. Or if it's a legged robot, it knows I have placed legs like I have placed, I am moving in a gate where I place legs like 10 or 8 centimeter across and I've taken 5 steps. So it has an estimate that I have taken around 40, moved on 40 centimeters. And then we have cameras where we say, okay, I take a viewpoint, I take an image and I keep moving my camera. So there is like overlap over images. So there is something called as a visual odometry. And there is something called as a LiDAR, which are like reflective sensors, where you take a LiDAR scan and then the LiDAR scan moves across. So we have like numerous estimates of the locomotion and using all that and the environment itself. So when we have a situation, we create the complete map. We have the map of the environment in the camera sense, we have the map of the environment in the LiDAR sense, and then all this information we use in a GPS denied environment to localize the robot. Now, something like 4 or maybe I was just still 5 years before, we used to write all the optimizers, all the differential equations and everything. Okay, this is the robot, this is the local, this is the exact location the robot is, and that's how it should work. But as of today, what the world is doing, what the Google, Waymo, the Facebook, Meta, and all these guys, what they are trying to achieve is, do we require domain specific knowledge to localize a system? Humans don't do that. If I had to come at this place, okay, I used the Google map to come to this place, but once I reached this whole environment, I could ask people and reach the place. I did not need to, I did not require a camera. I did not need to know something called as visual odometry. Okay, I as a principle, but anyone can do that. It doesn't require a domain specific PhD to do this. So why does a robot need to do that? That's a fundamental question people are trying to solve in 2025. So what they're trying to do, so there is something in 2020, what happened was a very, very smart guy formulated an architecture which was called as a transformer model, where it said, okay, there is an attention architecture that can train a neural network, generate a domain specific knowledge. So I think everyone here would have the knowledge of, like, would be using chat gpt or something, would have that understanding, okay, that is something which is happening across the globe. So what people are saying is, today in the world of language, what has happened in 2025, where the classical search, the Google search, is being replaced by a reasoning model, where a chat gpt sort of an architecture can actually reason locally. So it's sort of a person who knows a lot of things. 5 years down the line from today, or 7 years down the line from today, this would be replaced, or we will be augmented by a system which we call as a physical AI systems, like intelligent machines. Intelligent, it will start from robotics, start from mobility, and then ultimately would get into machines. It's like, can the machines understand itself and give and have a reasoning model to know what they are doing? So can it be extended to railways? I'm not sure. I'm here to just give you an understanding. Is like something like this is happening. In robotics, it's pretty closer. So that has been the case for in 1980s. We had this autonomous AMRs, wheeled robots doing autonomous navigation, autonomous stuff in 1990s, 2000, 2010s, increased to vehicles, increased to trains, aircrafts. Can they be autonomous? And now we have like self-driving cars starting to run. Similar paradigm. It happened in language. We are living that time where we have a reasoning model which can answer your questions without even going to the internet, replacing a Google search. 5 years down the line, 7 years down the line, people are working today. There would be situations where we would have actually intelligent robots. Today also we say robots are intelligent, but there are a lot of differential equations, a lot of things which augment that ability. It's not that the robot is trained fundamentally to do that. So the idea is, using transformers, would be a physical AI fundamental transformer model for vision, fundamental transformer model for robot control. So the idea is the system would have seen like massive data. So a set of system where it has seen lidars, it has seen cameras, it has seen a robot moving through this area, robot moving on the road, robot on the sea, robot in water, robot in the air. So it has seen multiple POVs, and it has seen, okay, if I see these images in sequence, have a latent understanding, have a latent thought, okay, this is what I'm doing. For example, as humans, if I am taking an aircraft, I know I am flying. So in similar ways, because of the POV, right, I see clouds. If I can also see clouds when I'm standing on the ground, but I have a different POV while I'm flying, which gives me an understanding, okay, I'm flying. So that requires, so when we talk about modalities, multimodalities, it means speech, text, understanding, reasoning, lidars, ultrasonic sensors. Different sensors can come together and give a single latent representation of the robot. Okay, this is what I have, this is what I am doing. Now once we reach that area, that okay, the robot knows where it is or what it is doing. So the next question that arises is what it has to do. So I have the knowledge, for example, taking from the human perspective, I know that I am standing at this place. Now the next question arises, what I have to do. I am being called here to speak on a fundamental topic, I have to speak. So how does the robot, how does the machine know that? So the next question is, it has to be trained to do a particular task, to do a particular objective. It's like either you train the robot in a simulator on a real world environment. So that's how like the robots are actually doing it, are actually being trained in our labs and like across the world. Across the world, robots are being trained to do fundamental journalist tasks. If I ask the robot, okay, give me an apple, or I am feeling hungry. So the question is, the robot should understand what does hunger mean, and what does the person eat, and how do you satisfy his hunger. You have to take for example, an apple from the fridge. The question is, where is the fridge? Before that, the question is, where is the robot itself? And how do you open the fridge? To open the fridge, you have to go near to the place, open the door. So all these things, either you teach the robot to do it, which is very difficult because it's like, so which requires massive amounts of data. It was easier in the context of language because internet was there. Internet has like massive data, massive contextual understanding of images to text. You have an image, so there's Wikipedia, there is like massive papers, books being published on the internet, massive like human centric understanding. There is bad data also, which is like people can write anything, people can type anything, but there is significant amount of data. But in the context of machines, in the context of robots, we don't know. I don't know how to ask a humanoid robot or ask a wheeled robot to give me an apple. I don't know that. The question is, can the robot train itself? And it can be extended to multi-robot fleets as well. It's like 100 robots. So we are doing it. We are already doing like a fleet of 200 robots doing a particular sortation task. The question is, which robot do what? They have to, right now they're coordinated. We solve a fundamental set of equations. We say, okay, robot, to maximize an objective, which suggests a task. Probably similar optimization architectures would be fundamental in railways as well. You have to take like maybe multiple trains have to be like, the lines have to be optimized, they don't collide. You have some high priority trains, you have some low priority trains, all the solutions would be developed. But over time, can it be task dependent? Can the solution come on its own? Can the device have enough understanding? Can there be peer-to-peer interaction? No human in between. Can two devices say, okay, that I am a little slower? Can the robot communicate to another that you do a particular task first? So all these systems, coordinated systems, can be trained. So people are, although in the initial stages, but what I'm trying to put across is probably the future lies into journalist robots, journalist system training themselves for localization, for their understanding of their abilities seen at that point, and also something called as reinforcement learning to control. When you know something, what do you do next? So we do everything. We do learning on the server, where we say we do a lot of things on simulation. We do learning on the edge, where a lot of these edge devices are put on the robots. They train itself, they collect massive amount of data and train what they have to do. It's like something like walking stairs, something like localizing itself and all. So similar to that, right? So when we, so uh, it's the same concept, but people are trying to put across into like very different domains. So something, so this is what we call it as a VGGT transformer, which was like published 6 days ago by Meta. So what they're trying to do is, I have a scene, I take significant amount of videos. I have no understanding how the video was created. I have no understanding how the situation was created, but I can reconstruct the scene for you. I can reconstruct. So for example, there are cameras around. You give the set of images. They'll reconstruct this hall and also tell you which camera was it, what was the focal length, and what was the situation, and where was the camera located. They would have, the model would have never seen the camera. The model would have never seen the situation. So right now it is limited to fundamental POVs. By POV means point of view, is like if the camera is like ground bound and all. Later they are trying to make a general purpose vision architecture where we say, okay, if I am doing this, if I am seeing this, what am I doing? So can I have a reconstructed point cloud of this and say, okay, there was someone presenting it. So that's what people are trying to do. And then that was just vision. And then again, Meta's work and NVIDIA's work, which I'm trying to put across, is like, can you have text plus vision? I say that I am a PhD in robotics, standing in front of a crowd, and this is the POV. So the obvious understanding is I would be giving a seminar on robotics. You say, I am a politician, I have this POV. Most probably I'm in a rally or somewhere like or maybe at a similar thing, but not doing a technical conversation. Similar from a robotics perspective, similar for a automobile perspective. You see a POV of a situation where there is there are like small kids moving across the room, across the road, and wearing like hats or something. You have a POV, this is a school area. The vehicle has the understanding, move slow. So that contextual understanding from images, so we can understand, we can ask the vehicle move slow when near a school. But the question is, how does it know it's near a school? So when you have this understanding, okay, from the image, from the sequence of images, you see something like school buses on the side being parked, small kids moving across. So there, if we can actually get a contextual embedding that, okay, this is near a school. And now the robot, the machine knows, or the car, or the autonomous car, or maybe some other vehicle knows what to do when it's near a school. Move slower. Allow more. Don't be egocentric. So there is something is like allow the other user to have more privilege. Let the kids walk across. So that understanding can actually make robots gain the real understanding of the scene. All these things cannot be modeled using differential equation. All these things cannot be modeled using optimizations. You can say the buses look white in Delhi. The buses look yellow in some other country. So it's not a color situation. It's that but we as humans can see the situation and can have a contextual embedding. So can the robots do that? So same is like text plus vision. And the other part is the next part. Once we have this understanding, okay, till now I was dividing the two parts. There is understanding of the scene, there is control of the scene. Now can you combine it together? I don't care where you are. I don't care what you have to do. The question is, can you achieve it? Can, for example, from a mobility perspective, from a railway perspective, or from a autonomous car perspective, the task is to move from point A to point B. There will be numerous situations in between. Can we create that massive data set, which we call as like a robot foundation model? Can we create a robot foundation model in such a way that they do the task? There will be a lot of situations in between. A lot of, for example, you cross a zebra crossing, you cross a red light, you cross a place where the road is not good. You don't need to characterize it. You don't need to make a decision. But is it the case? Can we train the robots end to end so that they make an action, make a decision automatically with all the sensors do they have? That the biggest problem with that is we don't have enough data as we have with, like, for example, large language models today of the internet. For every task, we have to teach robots, teach machines, gather the massive amount of data. But yes, the models, the GPU infrastructure is there. That's been proven using on like the GPT modules, the Gemini, and all those things. But the question is, for a physical AI perspective, or for a machine perspective, or for a mobility perspective, be it cars, trains, aircrafts, fighter jets, can we create that amount of data? Can we actually ensure that the robots are able to make decisions based on the sensors, not actually have those intermediate steps also? That is something that's the holy grail. But right now, can we even divide that into simple contextual understanding and make them enforce taking like either single robots or multiple robotic fleets, multiple vehicle fleets to actually generate massive, should actually generate good decisions of what to do, making human out of the picture? Because what and then what people are also tend to say is, do humans make right decisions for that matter? So that's where reinforcement learning comes into picture. Let the robots figure out their own best way to do things. It would be human trained plus robot trained itself, but yeah, there has to be some compromise. Yeah, so my thought was like, because me coming from a robotics background, having no understanding on railways as machines, we have understanding on mobility, to give you a picture of like what robotics is trying to do, trying to achieve like 5 years down the line. Maybe in a similar sense, uh, mobility, uh, large vehicle mobility, aerospace, railways would also want to do it like 10 years, 15 years down the line as well. But I think we have to start today to be able to do these things at that moment. So the language is there. The robotics would be there 5 to 7 years down the line. People are spending billions of dollars. The Google, Meta, the best in the world, they're spending billions of dollars onto this. Maybe that would be used into large scale autonomous. It has already transitioned into shipping industry, because shipping industry is slower, it's massive. uh, you don't need a lot of human made decisions onto it. But will it be be transiting to railways and all, is for the time to see. So yeah, that's what I wanted to say. Thank you.
Yeah, thanks, Doctor. I think that was a wonderful lecture. The biggest takeaway for most of us could be like classical models versus trained models. I think that is something which we wanted our engineers to be exposed to. I'm sure all of you must have been jolted a bit from your comfort zones. Yeah, good. Now let's invite Chirag Jain. He's the co-founder and CTO of Endure Air. He'll be speaking to us on Sense, Think, and Act. Chirag is a co-founder and CTO, as I mentioned, of Endure Air. He holds a BTech from IIT Patna and MTech in Aerospace, IIT Kanpur. A hands-on leader, he drives R&D in UAVs for logistics, surveillance, and industry. Known as the brain of Endure Air, he excels in flight dynamics, controls, and hardware-software integration, mentoring teams towards scalable innovation. He will be highlighting to us the perception, intelligence, and control framework, how PIC is transforming the mobility sector, and potential application of drones for Indian Railways. Chirag.
So, yeah, good morning, everyone. Uh, I feel honored to be present at the stage, to be talking about mobility and our experience in drones. I would probably be the youngest and least experienced speaker on the stage, and probably among the guests as well. So I don't claim that I have a lot of things and a lot of experience to educate the crowd, but still, with a limited experience which we have gained over the years, especially in drones and in the defense sector, I'll try to just highlight the experience and draw parallels in the railway sector, and how we feel drones can really transform the next the vision of safety in the railway sector. So just a little bit about Endure Air. So it's a young company, young startup. We grew out of IIT Kanpur. We were established back in 2018 in the labs of IIT Kanpur, where three of our founders came together and uh, had a vision of bringing these aerial vehicle abilities and using them for the betterment of the society and especially defense at large. That is where we started. Right now, we are a 150-member company based in Noida, and we have an extension in IIT Kanpur as well. We manufacture drones primarily geared towards aerial logistics in high altitude areas and also long range surveillance capabilities. So this particular PIC framework is something which I believe all of us here are pretty much aware of. But still, just to give a brief about what it is actually the backdrop or the background on which every autonomous system is based upon. For any measurable outcome, this is the framework which one has to follow, where an autonomous robot, aerial vehicle, or any platform would have the ability to perceive the environment, think intelligently, and then act accordingly. So in this framework, of course, the first part is the perception part, where you have the sensing element, which comprises of various advanced sensors like LIDAR, thermal cameras, RGB sensors, and other stuff, which sense the environment and finally give it to the autonomy unit, the brain of the vehicle, which brings, so just for an example, when a drone detects a cracked rail or an overheated junction box before human eyes can. So that is the idea where the aerial vehicle is actually, sensing and perceiving the environment before human eyes can actually enter. The second part is the intelligence, where the one has the capability to make sense of whatever data it is consuming. And then the third part would be the control part, where it's the physical movement of the platform or the action which can be generated from this intelligence which one has generated. So, for example, would be that the drone scans 10 kilometer autonomously, generating alerts and uploading that data live back to the servers. So here, just want to talk a little bit about what kind of mobility solutions are already existing, just for an example, in other sectors. So in automotive, an example would be the advanced driver assistance systems, which use these varied sensors, LIDARs and cameras, and AI on top of it to drive intelligent collision prevention algorithms and help users to safely traverse these ever-changing environmental requirements, some of which my previous speakers have already talked about. Then we have an example in metro and urban rail scenarios, where we have autonomous metros operating without any driver assistance, and where you have the onboard perception systems and control algorithms to optimize the energy, crowd flow, and timelines of these vehicles. Similarly, in the drones and aerial platforms, we have the PIC stack, which empowers our drones to autonomously fly, autonomously plan their missions, reroute accordingly, and then successfully execute and generate intelligent data, which can basically act as a backbone for other important analytics and basically other important intelligence can be awarded and action can be taken accordingly. So these are basically used in agriculture, mining, and also disaster response, and now more critically in infrastructure inspections as well. So this just highlights on a broad level what this entire architecture looks like in a drone sense. Basically, you have the drones which have the onboard sensors like lidars and cameras, where you actually monitor, capture the data live or record it, and that is the active sensing element. Then you have the onboard AI processing. You can choose to do it onboard, or you can transfer these data through a telemetry back to the GCS through a live line of sight link, or through a SATCOM link back to the ground station, where advanced analytics can be run. It can be either a human in loop, it can be completely autonomous, and that is the general framework in which a typical drone operates. So what are these sensors, for example, currently in the drone sector? And especially which ones might be useful in a railway context? These are some of those. So right now the drones are which people are operating or which are currently existing, they are much advanced compared to the ones we probably had seen 5 to 6 years ago. So in these 5 to 6 years, the drone field has rapidly evolved, and now they are not just hobby grade drones, which one probably operates in marriages and stuff for videography, but it can carry very advanced sensors, lidar cameras, thermal sensors, RGB cameras, multispectral, and even radar sensors, synthetic aperture radars, to generate very precise and very rich data set on which the analytics can run either on board or on the ground station side. So what can we do with lidar? Of course, this has been this is something which has been heavily used right now in the mapping and inspection industries for doing centimeter level precision mapping. We have thermal and IR cameras which can detect heat and all anomalies. It can detect humans for crowd flow and crowd control. You can have inspection of railway tracks or components or machines where the heat anomalies can be detected, and the right action can be taken accordingly. Of course, you have the RGB cameras, which are mounted on highly stable gimbal platforms, which enable you to monitor from a very far standoff distance, more than 2 kilometers. You can monitor without interfering with the actual site you're trying to monitor. With a standoff distance, you can monitor your surroundings and generate alerts accordingly. You of course have multispectral cameras, which can monitor vegetation growth, right of way requirements, and all of that you can monitor, detect easily, and take actions accordingly. And then you have radars for synthetic aperture radars and all, which have the capability to operate even in areas where your normal RGB cameras might not work. It has the ability to penetrate fog, dust, and low light conditions, and still give you reliable data when the other sensors fail. So all of this, the current drones have the capability to lift and seamlessly integrate with any other applications or any other sensor and intelligence and analytics network. So coming to the intelligence part, what we feel the possibilities are with the current technologies in place. We can do defect detection, where the drones there are low flying drones which operate close to the railway tracks, and highlight these cracks or misalignment or even rust formations in these structures even before a human can come in the loop. You can do volumetric analysis using lidars and simpler cameras, which can possibly be used for volume measurements, and by that you can probably estimate how much you're transporting, how much goods you're transporting each day. You can also monitor whether there is theft happening, or maybe there's an uneven distribution of the load. All of this is seamlessly possible through current drones and drone technologies. Of course, you can use multispectral or hyperspectral cameras for vegetation identification and classification. And this can help meet the right-of-way requirements, overgrowth, prevent overgrowth, and other stuff. Then you have, of course, object recognition, where you can identify walls, pipes, and other stuff which you would probably want to do. So this is just a typical example of what kind of intelligence exists and are being used for other applications in the drone sector. Then in the control system, you have various abilities which the current drones possess, which you can leverage upon for your application. You have precise navigation, which includes RTK capabilities, which gives you centimeter level precision. So you can pinpoint very exactly where an anomaly might be taking place and where you need to specifically act. Right now, the drones, all of these drones are highly autonomous. Of course, not to level 4 or level 5, but at least up to level 3, these drones are operating quite well these days. And you have the ability to either run autonomously or have human pilots in the loop for intervention and stuff. Right now, the drones which we have, they are VTOL capable. VTOL essentially means vertical takeoff and landing vehicles, which means they don't really require a runway or anything to act or to be deployed. And they have very good hover stability. So you can precisely hover for hours at end on a typical spot and keep monitoring a single point of operation where you might want to operate. And that too in heavy gust conditions. Of course, the current drones have very good fail-safe redundancies as well. In the recent regulations in the drone sector have enabled the current drones to be very much more mature and reliable than the earlier generations. And all of these drones actually have parachutes and other systems on board, which ensures that there is no loss of either the man or material or anything which is being operated. And of course, some other aspects would be these drones have fail safes on either battery going low or signal loss or any other condition. Then the capability to integrate multitudes of payloads like the ones which I've already described. So in this particular slide and subsequent slides, I thought of just giving a highlight of what we feel are the key areas where drones can play a crucial role. This is our understanding and our perspective. Of course, we have not really dealt with railways before. We have majorly been focusing on defense and some other civilian sectors. So please forgive me for any misrepresentation or something. But talking about the first application, the uneven loading in freight trains. Right now, there's a problem which we understand there that there can be situations where the loading in the train, in the freight trains, is uneven because of maybe jammed doors or some other scenarios. And this creates a lot of stress on the, I believe, the axle and other platforms. In this case, the drones can play a very crucial role where they can fly autonomously over the cargo wagons and do a volumetric estimation and give live updates back to the headquarters. And there one can assess whether the volume or the shape and of the wagons and the materials inside, whether it has shifted, it is uneven, or some action needs to be taken accordingly, or even for theft prevention for that matter. And this is a capability which one already has in the current drone industry. The other is, of course, trespassing and vandalism, where you have the general surveillance requirement in defense, where you have RGB and thermal cameras, which can autonomously detect humans, detect movements, and generate alerts accordingly. Even on top of this, right now we have the capability of using drones with a live tether, uh, which enables these drones to actually operate continuously for 8 to 10 hours or on end. Uh, so you can get a live 8 to 10 hour live surveillance without having to refuel or land, which is a very interesting ability to have for live monitoring in, let's say, a disaster hit area, or even platform monitoring and crowd control. The other application which we feel this can be useful is yard management, where you have to track the wagons, the number of wagons, where it is, the location, and also monitor the material, the movement, daily tracking, inventory tracking, and the stuff. Now, this particular entire application can be fully automated. You're using a concept known as a drone home, where you have an autonomous drone docking station which is fully enclosed. You can set the time key if you want to do regular inspection at, let's say, 7 a.m. in the morning each day, and generate some pre-programmed reports. Then at a single click of the button from a person in the headquarter, you can just ask it to do it. The drone home opens up, the drone autonomously takes off, does its routine inspection, comes back and land, uploads the data autonomously to the headquarters, and gets charged in the process through the drone auto charging features which we have. So no human in the loop, no intervention required, and you generate live insightful reports each and every day regularly. And so this is a capability which is already deployed in some other industries, and it is actively deployed in some key foreign countries as well, and which we feel would play a crucial role as we go along in the Indian context as well. The other abilities is, of course, inspection of bridges and tunnels, where you have close flying drones doing inspection of rust and other cracks and defects. This is also already being used as we speak in some other industries, and would be key in this railway context as well. The next one, the right-of-way management and vegetation overgrowth, where you can use multispectral cameras and even normal RGB cameras for that matter to do continuous monitoring for meeting the right-of-way requirements. We currently have drones which have the capability to cover 180 to 200 kilometers in one stretch. And these are smaller drones, not big drones which you require. So 200 kilometers of right-of-way can be covered in a single stretch, which gives you tremendous opportunity and time savings and cost savings, which we foresee. Of course, there is the emergency response, where some interesting ideas have been floating around in other countries, where these tethered drones, especially heavy lifting drones, can be deployed for lifting either megaphones or searchlights or other sensitive equipment in these disastrous hit areas where derailments are there and stuff, to provide uh, lighting environment and to coordinate the search and rescue in these critical areas. So, of course, these logistic drones can also be used for material movement and emergency goods movement in these particular disaster hit areas. The track defect detection I already mentioned. Other than that, it would be to monitor the work progress, which I mentioned in yard management, where you can do all the inventory tracking and material movement live, to do all the volume estimation, inventory planning, and some other insights which one would need. Then, of course, one can be go even one step further and probably do track alignment monitoring, and other stuff. Of course, this may be futuristic, but we feel, I mean, it has also a lot of potential as we go along. So just talking about what kind of drones we have. Right now, I mean, when the word drone is spoken about, the imagination generally turns to these small quad rotor drones, which we generally see in marriages, these smaller drones, and which are doing photography and stuff. But right now, the drone landscape has expanded far beyond those simpler drones. So the ones which we manufacture can be called as small autonomous helicopters, like the ones you see over here. We have drones ranging from sub 250 grams all the way up till 150 grams. And these cover multitude of applications from surveillance all the way up to logistic transport. So the first one which we have, it's an ALAC. It's a smaller drone like the ones which you typically see for rapid deployment and surveillance. The other ones which you see over here are for long range surveillance and high endurance applications, where you can cover 100 to 200 kilometers in one stretch. Then you have tethered variants of the same drones, which gives you the ability to continuously hover for 8 to 10 hours, as I mentioned, and do live surveillance of a particular area. Then we have our logistic series. This is our primary product, and actually we are the very few players in the industry who have these capabilities. So with these abilities, these kind of drones, we are able to lift 50 kg worth of 50 kg load in high altitude areas upwards of 5,000 meters and beyond. So these areas would be in Ladakh and the eastern perimeter. And these 50 kg load can be transported autonomously to 10 kilometers and beyond. So this 10-kilometer lifting capability, 50 kg lifting capability, it's not just for your normal goods. Of course, normal goods is one thing, but you can lift very advanced sensors as well. So just for an example, in a defense context, we have electronic warfare payloads and all that, which can be integrated with these heavy lift drones. And that gives us the ability to monitor these critical areas and sites. But that in the same context, for the railway context, we can lift some other payloads like searchlights and megaphones and some other critical sensors, which might not have been possible earlier, but it is possible now. So this is what we do. Of course, here just wanted to cover, I mean, what we have seen in the global scenario, what kind of applications are being targeted by drone. In fact, I mean, in this BNSF railway, which I was mentioning, inventory monitoring and track inspection is something which they are already experimenting with, and which we feel can be done over here in India as well. Similarly, in Netherlands, we have seen switch point monitoring, which probably would be an issue because of it being a very cold country. So where they do autonomous monitoring of the switch point, the drone flies over there and identifies whether the points are stuck and turn on off the heaters accordingly. This can be a potential problem for us, maybe in the northern section where our railways might be operating, but I'm not the authority here. I mean, would love to know your experience here. Then, of course, in UK, you have emergency response, which is being handled by drones right now, or at least being explored in that context. So, a lot of these applications plus a lot of other applications are possible, which we foresee using drones. So, I've already covered a little bit, but our drones essentially, I mean, they have long range and endurance capability, which basically gives railways the capability to do linear asset inspection for very long ranges. And of course, a lot of payload integration is possible, not just for our drones. In fact, I mean, for many of the drones operating in the space. These drones are VTOL capable, vertical takeoff and landing, which does not require runways. And of course, these are autonomous and repeatable with very low deployment times. These are just some of the technology stacks on which our drones are built, which are unique to us compared to all the other aerial vehicles which you see outside. So it's a novel variable pitch technology, which is used in helicopters. We are the ones who are miniaturizing it and using it in drones. And this gives us the capability to be much more efficient, have much more gust resistance, and much higher speeds compared to your normal drones. Of course, we have multi-sensor fusion, where we have RGB, LiDAR, and other cameras, and we fuse together to generate some valuable intel. The fail-safe features, as I mentioned, I mean, the parachutes and communication failure and all those are already inbuilt in these drones to make them much more reliable. And of course, I mean, just to highlight this point, the MR today, I mean, he also highlighted, I mean, the criticality of safety in this particular sector, which one has to focus on. And that same safety paradigm is something which we also take forward in drone field as well, where safety is paramount, safety of system and safety of the humans operating or the people which are nearby. Because as an aerial, because just like railways, I mean, we don't have a lot of scope of failure. It's just one failure and the drone crashes. I mean, this is not a situation which one can have. So to mitigate that, I mean, there is a lot of safety features already built in on some various levels, some of which were already highlighted by the earlier speakers. So we carry the same safety paradigm in our developments as well, is what is the point which I wanted to drive home. Then the other features which is special to our kind of drones is that the time on target is much higher. And what do I mean by time of target? It is essentially the ability to go quickly to a certain area and keep on inspecting that area for a longer duration. So that is only possible because of the high speeds of the drones which we have compared to your normal other drones which you see in the market. And this is a very crucial factor for generating any meaningful insights. And of course, the edge AI capability which the current drones have. Since we have a lot of lifting room, we can carry a lot of high-end compute on board with us to generate real-time analytics on the edge. So this is the capability which we currently have. So with this, would like to just close this. Thank you very much for the time. Thank you, sir.
Yeah, thanks, Chirag. I think we'll take the questions towards the end. Now, after having this cross-sectoral use of PIC, we'll come somewhere near to the railways now. And here we have today a special guest. In fact, he flew down from St. Petersburg in the morning at 3:20 and especially came on our invite. Mr. Popov Pavel. He has been a dear friend for the last many years. And a brief introduction about him. Popov is currently the director of St. Petersburg branch of NIAS. NIAS is a Russian RDSO equivalent, but they have around 100 PhDs who are working only with him. You know, he's the chief constructor of the autonomous trains in Russian railways. And as I mentioned in the morning, these are already operating in Moscow Circle. We had actually seen this when we were there in Moscow in February. Popov is the leading the Russian Railways autonomous train initiatives, and he is an expert in railway automation, digital signaling, and AI-driven rail solutions. He spearheads the development of advanced train control systems and autonomous operations and shaping the future of Russian rail transport. I will, half an hour is not enough for autonomous trains, but surely tomorrow I think we'll spend probably in half a day to try to understand, get more insights from him. But for all the CRIS engineers here, I present you Papao, please.
Good afternoon, everyone. Thank you for the invitation. First of all, thank you for introduction. And of course, I am glad to share our experience about my favorite topics and some information about me. My first presentation about autonomous train was in Milan 7 years ago. I started since 2016 the auto system for Russian railways. Long period, a long way for us, a lot of innovations, a lot of challenges we met during our way. And some information about NIAS, yes, Kumar is right, it's a subsidiary company of Russian Railway, we're responsible for R&D, research and development for Russian Railways. And our main stages, and we started with shunting locomotives. In 2017, we started testing different sensors, lidars, radars, cameras, and then we set a sensor for commuter train, Lastочка, 2019, and only 2024 we started passenger operation, Great Automation 3, and in this summer, in June, we started operation of autonomous shunting locomotive, the Marshall Yard Luzhskaya. And of course, a lot of open challenges, and in my understanding, maybe 95% questions were resolved, but not all of them. And I will explain what we did, what is necessary to do in the future. And of course, basic question, it's about technical vision. What is an obstacle? What is necessary to detect? And of course, the first approach was that it's necessary to detect obstacles at the distance more than braking distance. And you know, for example, high-speed train for freight train, it's usually 2-3 kilometers. And our question was, what about human capability to detect? And of course, a lot of conditions about weather, about light, and how to check system. And for our system, it's necessary to open on all of these questions. And only in 2033, we decided to check human capabilities to detect obstacles like pedestrian. And we took 10 human train drivers and set ahead of them obstacles and check the distance of detection for human. On average, you can see it was 333 meters on average. Maximum, it was 500, or maximum it was 600, and minimum 106. But of course, for perception system, result is much better. And it was result 2 years ago. Now, of course, result is much better. And the same about time, perception, technical vision always works earlier. But you can see in average 2 years ago, our system was 70% better than human. But it's only for detecting standard obstacles, which it's, you know that it's necessary to train a system. It's not simple questions. And you can see next questions, how to check the system. And no standards for railways. And for automotive areas, there is some standards, but only 4 different targets, diameters. And a lot of examples, for example, in Germany, it's Hawkins and obstacles, core, ships, different examples. But of course, it's very important for us to resolve question how to test and develop some standards. And you can see, for example, some from automotive road vehicles, and we have a dedicated project to develop obstacles and how many obstacles, and also standards, how to provide test, and how many obstacles it's necessary to have. And inside of every obstacles, we have special electronic equipment like a GPS receiver, because it's necessary to check real distance between vehicles and obstacles, because it's very important to have a real distance, and based on this distance we make braking curves to stop our train ahead of obstacles. And of course it's necessary to check system in case of, for example, fog, smoke, and siege light. A lot of different situations are possible. And for any obstacle which we have, our system works better because we have special data set. We train our system better than human. But you understand that number of obstacles unlimited. And of course, there is a lot of different approaches, and possible, for example, to find some anomalies on the track, but it leads to false positive. It's another questions. And I remember 5 years ago, I wrote an article dedicated false positive for perceptions. It's not easy questions. And for your understanding that our system better than human for standard obstacles, but the main problem is to detect a situation like on the picture below, for example, track ejection, flooding, and the problem that it's very difficult to collect data set, sometimes impossible. And our approach now based on synthetic data set, and we have simulator and train neural network on synthetic data, and we have special polygon to check this situation like track ejection. But we can check only 1-2 times because it's very expensive to test such situation. And for your understanding now, it's very easy to implement technology for detection, for example, pedestrian. I think every student can do it. To install camera, to write software, a lot of library which is ready, but to realize safe system and to provide safety, of course, a lot of additional efforts it's necessary to implement. And of course, we have simulator. It's another project, and we have software in the loop, hardware in the loop, vehicle in the loop, and a lot of tests, and it's included in our CI/CD development. It's very important for us to have simulators and to improve realism of this software. And the next, it's necessary to understand that human has a lot of information about different situations and analyzes the book evidence psychology, and an average person consumes about 394 petabytes of information. For comparison, our data set consists of several terabytes. And it's necessary to understand that for obstacles which system trained is much better than human. But on average, human in some situation better than technical vision. But every year, number of data is becoming more and more, and I am sure it's soon technical vision on board profession would be better than human in all possible situations. But the task for us and, for example, for our competitors is to collect as much possible data for training. And of course, not enough sometimes to have only perception. For example, human consumes 90% by vision and 9% based on hearing. And our next task is to add information and to add sound analyzing. And of course, it's maybe better to use approach based on multimodal And we use, of course, transformers, a lot of different approaches. But the next task is very important, is to prove safety. And now we are testing, for example, sound detections, different sounds. It's necessary only, of course, for grade of 4 for full autonomy. And for your information, it's very important to have data set, railway data set. As I know, about 7, 8 open data set, one of them from my company, Russian Railway Transport data set, a lot of data set from Germany. I remember the first data set was from Austria and was published in 2019. But it's not so simple because it's necessary to have a rule and labeling guide, for example, how to prepare. And I'm sure that it's better to have some standard how to annotate data. And I know only 2 open annotation guide, one of them from my company and the second from Germany, labeling guide. It's about collecting data. And of course, now, for example, a lot of different data sets from different company, but it's very difficult sometimes to use and to combine data from different data sets. And for example, it's about annotations, for example, tracks for semantic segmentation, about objects and so on. And the document consists usually 100, 150 pages. It's only how to annotate data for training and how many data is necessary. But even if our train autonomous, we need additional control. And it's some examples. Left side example from our project. Because, for example, if we have some obstacles ahead of train, our train would stop automatically. And what is necessary to do after that? It's necessary to inform our operator, and operator will decide what is necessary. And we have document which describe in which situation operator should react, what is necessary to do. In general, operator only supervise without any interventions. But in case some failure or some obstacle detections, we need some reaction from our operator. And for example, we have new profession, train driver operator. And we have 2 different console for operators. First is all like a cabin, but second, it's only one monitor, a lot of information from different systems, for example, from ATP system, TCMC system, and information from video cameras. It's more convenient, and we investigate different approaches, and we tested with real drivers how to control remotely train. And same approach not only in Russia, but in the world. For example, you can see example from Switzerland, Netherlands, Germany. Remote control is becoming widespread, but the main question, of course, is communication technology. And now we're using 4G. And for example, Russia is a very big country. For distance, for example, between east and west, we're trying to use satellite communications. And for us, and possible to combine satellite and 4G communications. But without operator, without human in the loop to supervise, for us, autonomous technology is impossible. And we need to somebody to control. But it's very important to understand all possible situations. And for example, we analyze different scenarios and behavior, for example, dispatcher, train. And after that, we write how our autonomous system should work. And after this investigation, we realize that it's necessary to have additional people, which we called fast response team. In case of train failure, we need to send fast response team to autonomous trains. And we calculated the time of arrival. It's less than 10 minutes for our project, Moscow Central Ring. And for example, sorry for Russian, usually now it's voice communication between dispatcher and train driver, but if our train is autonomous, no voice communication. It's necessary to change rules. It's necessary to develop new software for control. and we have additional project. It's new software for dispatcher, how to control, and we have train operator which interact with train dispatcher and autonomous trains. And next, it's necessary to collaborate and to check perception. And we have additional project to check camera, lidars, to calibrate them in our depot. Of course, a lot of questions connected. It's not in my presentation. It's about localizations systems. And for example, main approach for our systems is to recognize our track based on segmentation neural network and recording our track to find obstacles. But sometimes in Russia, our track under snow, impossible to recognize track, and we need to use digital map, digital infrastructure, high precision localization system, which based on fusing data from odometer, inertial navigation system, and also SLAM, vision SLAM, and satellite navigation. But a lot of problem now in Russia with satellite navigation because it's widespread jamming, spoofing, and we need additional software which control to avoid influence of jamming and spoofing on satellite navigations. And I believe, of course, that autonomous trains are not the future, it's reality. And the first project which we start operation, it's shunting locomotives, because maximum speed only 25 kilometers. It's a limited area. It's easy to send a fast response team, for example, to repair in case of failure on the locomotives. But a lot of interaction now between autonomous locomotives and human. For example, it's necessary to couple, to decouple wagons. And for example, we have a separate project for developing robots who can decouple wagons. And it's communication between robots and autonomous locomotives. It's communication between human who can decouple wagons and autonomous robots. And of course, sometimes in marshalling yard, train can move with wagon ahead. We had additional control based on stationary vision cameras. A lot of open questions. But in August, there is a big exhibition in Russia, and we will demonstrate our projects for shunting locomotives. And the most important, based on our experience, that introduction of autonomous trains requires a fundamental revision of the operating technology. We need to change operation technology, like my example about voice communications, no voice communications. It's new rules, how to communicate, how to organize operation, and of course, a lot of IT system. For example, after switching on train set connect to special server to download schedule, and based on this schedule and based on system from radio block center, he will move according to schedule. And also questions how to connect onboard perception to train system inside of train. It's connection between, for example, ATP like Kavach and the perception system. Usually we send to our ATP distance to the obstacles, and after that ATP make curves to stop trains in advance on obstacles. But for us, of course, advantage of introducing autonomous train and main benefits, and it's very important for Russia, it's labor shortage. For your understanding, Russian Railways approximately has 150,000 train drivers, and not enough. It's very difficult to find train drivers, and we need to develop autonomous system for shunting locomotive, for mainline locomotives. And next very important questions, it's questions about safety and reliability. And I remember a first presentation about Honeywell that it's necessary to increase the reliability. And we have the same problem. But every producer of every system on the train tried to increase reliability, and after that to install additional system, and after that my train was becoming very expensive, like gold. And first of all, of course, safety, and safety is the first place. But reliability we started to discuss, because sometimes it's possible to stop train and to send fast response team, and it's questions of discussion where reliability is important, where is not necessary. For example, for shunting locomotives, sometimes it's not necessary to increase reliability, only safety, because we can send response team to the train, special people, it's engineer who can, for example, repair some failure. And next questions, how to prove safety of neural networks. It's very complicated questions, no open answer. We have some approach how to prove and how to validate our perception systems. And but a lot of open questions for collaborations, especially it's standard how to test such system, which protocols is necessary to use for interaction between different subsystems. And we're ready to collaborate. I hope we will have tomorrow discussions about open questions, and I'm waiting for your questions about our projects, and not only for this project, but for another projects. Thank you.
Thanks, Pavel. Now, I think we'll have more insightful discussions and detailed discussions tomorrow. I think there was a great presentation on autonomous trains. And now we will actually be coming to something closer to perception, intelligence, and control in rail systems in India. I think I would like to first invite Lalit Mansukhani and uh, his deputy, Mr. Nagraj, for the presentation on Kavach, enhancing train safety and efficiency through unified braking algorithm and Kavach. Let me give a brief introduction of Mr. Lalit Mansukhani. He is an IRSSC 1991 batch topper. He is the Principal Executive Director currently working at the Center of Excellence for Kavach in the Ministry of Railways. Formerly at ISRO and UK Railway Signal Design House, he is the official chief architect and inventor of Kavach, a multi-source interoperable train control system. His innovations in radio communication have enhanced safety and operational capacity. He will be highlighting to us the progress of universal braking algorithm of Kavach, developed by COE for railway Kavach technology, in addressing the challenge to have optimum train control, addressing both safety and operational convenience. Nagraj, his colleague who's working in COE as well, is an IRSC EE 2009 batch officer. He's a BTech in electrical from SV University Tirupati and a master's from IIT Bombay. At present, working in Center of Excellence in the areas of onboard Kavach and braking algorithm. Now, the floor is given to Mr. Mansukhani and Mr. Nagraj. Yep.
Thank you, MD Chris. First of all, greetings to CRIS fraternity for the Foundation Day and all the people present over here. And it's privilege and honor for us to be part of this event from Center of Excellence for Railway Kavach Technology site. Just during break, there was some curiosity about what is COE and all. Let me just briefly tell. Center of Excellence for Railway Kavach Technology is a Indian Railways unit, recently, a couple of years back, established to carry out R&D and further development of Kavach, apart from help developing the ecosystem by training and interaction with academia, industry, handholding of stakeholders, etc. So coming to the topic, Actually, as we can see here, we have tried to tailor-made our presentation to, the three keywords which are mentioned probably here or here: perception, intelligence, and control. So that is what our presentation will be focused on. That ultimate aim of ATP is to, carry out braking, but it should be optimum. Okay. And my previous presentations presenters have really done wonderful job. George mentioned about Kalman filter, in which prediction, correction, and update is done. Chirag also mentioned about sensing, think, and acting. So our presentation also will be something like that. So just to tell what is peculiarity about Indian Railways environment, actually we know that India has unity in diversity. Likewise, Indian Railways also has got, very diversified rolling stock, fleet of rolling stock. A lot of, variants are there. Where in Europe we can say we primarily have got predominantly coaching traffic, and in US we have got predominantly uh, freight traffic. But in Indian Railways we have got mix of both. Here I have just tried to list down the combinations of rolling stock what we can have. You can say types of locomotive list is still not complete. And then we have got a lot of varieties of coaches, then wagons, and each variety also has got a lot of sub variants with different braking characteristics. For example, among Boxen itself, we'll be finding a lot of varieties. Then really braking would get impacted by, uh, like the order of sub variant, whether it is in the front end of the train or it is towards the rear end of the train, and how does it affect optimum braking. Doing braking is something, but having optimum braking, because we are talking about autonomous train operation today. So optimum braking will be our focus. And yeah, so so this is just to give a glimpse that we have to cater all these requirements. We have to have optimum braking from safety point of view, which is not to be compromised in any way, but at the same time it should not affect operations also. It should be operation friendly. So it is bit technical presenter, so I will hand over from here onwards to my colleague Mr. Nagraj, who is the person who has devised these logics. And it will be quite interesting. And let me just mention that it is something unique kind of algorithm or approach, braking approach, which we have tried to capture all the kinds of possible combinations in different situations, different terrains, and with a different um, rolling stock and all. And it has been tested in field also successfully, let me humbly mention. So over to you, Nagraj, please carry on.
Thank you, sir. So in any conventional or any train control algorithm, so the basic model is that how the braking happens. When the loco pilot drops a BP in the loco, how the brake wave will propagate along the length of the train. That is the basic crux. And using this, driver is given different levels of braking. Generally, in trains, we have a brake pipe pressure of 5 kg. Then driver can apply any brake between 0 kg to 5 kg. That linear application of brakes as per the requirement of driver is possible in the normal driving by loco pilot. But when the train control algorithms, they cater to emergency situations. We should not apply or routinely apply brake whenever loco pilot is driving. Loco pilot continue to do his driving, and whenever it is required, that means whenever an emergency situation is declared or detected by the Kavach system, then only we should intervene and apply the brakes. So Kavach generally is having two kinds of brakes. Normally we have full service brake and emergency brake, and normal brake is used in very rare conditions to apply the brake to control the train. So we have a brake model. What is the brake model? The brake model consists of the time taken once the brake command is triggered in the locomotive, the BP dropping in the locomotive happens. And now this wave propagates along the length of the train, first coach, second coach, third coach, and it propagates till the last coach. So how much time the brake force travels along the length of the train, and how much distance train will travel. So this has to be catered into the model. So we have a two-step model. First one is brake propagation time. That means when you apply a brake, for some time there will not be any application of brake in the train. So that is the TP model or train propagation time, and then the brake force linearly generates along the length of the train. So this is the basic model which we use in the train control algorithms to compute the braking distances, and based on which driver will be generated certain profiles which he need to follow. Suppose he is approaching a target of 80 kmph when he's driving for 140 kmph. To negotiate from 140 kmph to 80 kmph, how much distance he needs to apply and how much extent he need to apply the brake. That is to be computed two different levels. One is full service brake and emergency brake. That is what the basic algorithm does, or basic model does. These are the measurements. Generally, if you connect a pressure sensor to every coach, and you connect a pressure sensor in the leading locomotive and measure the timings. So you apply full service brake and you measure the time every time how much the brake force is generated along the length of the train. So that you plot the curve. So the previous curve, whatever we have seen, is a linear approximation of the curve which we are seeing practically. This is the practical measurement. If you measure in every coach how the brake force is developing, these curves will populate. So we have done this experimental measurements of these timings. So different combination of rakes, and then these values we have captured. So these will be a preconditioned data which we will feed into our algorithm depending upon the length of the rake. So this is how the train length and type of consist is taken into our consideration. This is the speed dependent acceleration model. This is again coming from basic physics. Suppose the friction will be the coefficient of friction between the brake block and the wheel will be higher at lower speed and will be lower at higher speed. So when you try to control the train from 140 kmph to 0 kmph, 140 to say 70 or 80 kmph, you will have very less brake force because the coefficient of friction is very less. But when the lower speed comes, the coefficient of friction abruptly increases, which will be invisible hand inside the physics, and that will try to give excessive force. This is the reason most of the train control algorithms in the lower speeds, they control excessively and stop too far from the targets. So that factor also we have considered by using this speed dependent accelerations. So these are the practical considerations which we use in our model. So all these models are computed well in advance before feeding into the locomotive. What is the time taken for the full service brake? What is the time taken for the emergency brake? This also incorporates the brake rigging arrangement. Some of the coaches will have multiple, suppose power car of LHB is having some brake rigging ratio. Some conventional ICF coaches are having different kind of brake rigging ratio. So all these factors are considered, and we pre-compute the deceleration constants which are applicable for the full service braking and emergency braking. And similarly, availability of special features such as in LHB rakes, we have brake accelerators. These brake accelerators will have impact on the emergency braking. You will have quick brake application along the length of the train compared to ICF coaches. So this factor also we factor out by that experimental measurements, and we use these to compute the pre-configured parameters. So how we arrive deceleration constant is in line with the UIC 544 bar, that is brake power calculation, so that we use to compute these parameters. Once this is done, this is the, so far whatever we have discussed is the conventional train control algorithms which are popular. So the purpose of ATP is to, when the locopilot is able to when the coverage system is able to understand that the signal approaching is a danger, and if the locopilot is driving excessively, the excessively means that depends on braking distance. For Vande Bharat, the braking distance may be 1200 meters at 160 kmph. For LHB trains, 22 coaches, it may be 1500 meters before the red signal. So depending upon these braking calculations, the system will apply the brake. So this methodology or this approach is good as far as the prevention of SPAD is concerned. Why? Because we are only concerned to stop the train before the foot of the signal, and we don't bother whether the train is able to negotiate further because there is no movement subsequent to stopping the train. But when you consider to negotiate a speed restriction, say 100 kmph, 140 kmph to 100 kmph, now you have released the brake around say 110 kmph. But once the brake command is triggered to release the brake, that doesn't mean that the train is going to release the brake instantaneously, because the entire air has to be recouped in the length of the train. As the length of the train increases, the time taken for the air to recoup along the train also increases. So this factor is the new approach which we have taken, because conventional algorithms are giving troubles due to this excessive time taken for the brakes to release. And if you see this one, this is the comparison of 59 box and rake. If it is a single pipe and twin pipe, if the red curve is the single pipe and blue curve is the single red curve is a twin pipe and blue curve is a single pipe curve where the time taken for the brake release is excessive. So what will happen because of this? Even though you released the brake thinking the train will negotiate or coast the target speed, it will try to stop because excessive brake force is still available in the train due to the time taken for the releasing of brakes. So this factor we have considered in our algorithm. This is a new approach which we are going to introduce to optimize our braking. So this is another problem. The conventional train control algorithms always consider that the gradient on the approach of the train to be modeled in your calculation. Suppose if you consider this classical example, the gradient on the approach of the train is a down gradient, but predominantly the train is on the up gradient. So this is practically applicable for freight trains where the train lengths are higher and speeds are lower. So the braking distance are almost equal to the train lengths or little more than the train lengths. So what is happening? The physical gradient occupied by the train is more affecting than the gradient you are going to approach. So we also consider that gradient from the rear of the train in some cases so that we optimize the braking. So these two factors we have modeled new into our approach to decide where to release the brakes. So this is the basic philosophy. So this is called as release time optimization or release optimization. So the conventional curve where we have started, the algorithm only considers the time taken for the brake to apply and how the brake force is building. But we also wanted to consider that the time taken to release. In this curve, if you see the blue curve is the BP and red curve is the BC. So when you drop the BP in the locomotive first portion of the curve, so you have a reduction in BP from 5 to 3.5 and the brake force is linearly increasing from 0 to maximum. That is the cumulative brake force of the train. So we have added every coach or every coach brake cylinder pressure summed together. That is the curve we have presented here. Now when you release the brake, that means when 3.5 to you recouped the brake to 5 kg, then instantaneously the brake force cannot be 0. Still you have a substantial time the brake cylinder pressure in all the coach to release. So this is the time in which loco pilot is also not able to accelerate the train because unless BP is more than 4.75 and the loco's brake cylinder pressure releases, it will not allow loco pilot to enable traction. So this has an impact. So if this kind of approach is not considered, then in the loop lines you have a problem because you are able to reduce the line capacity because train will continue to reduce its speed because the substantial time is taken in recouping the air pressure. So this is the optimization which we are trying to do and we have done as far as passenger trains are concerned so far in the field. So this is the new approach. So what we will do is we will apply the brake considering the conventional train control algorithms when the speed of the current train is beyond the full service brake limit, then we will trigger the full service brake. When the speed of the train is more than emergency brake, then we will trigger the emergency brake. But now to handle this variability and the amount of force which is going to be retained in the train, even the brakes are released. So we have come up with the new curve. That is the this curve you can see here. There are two dotted lines. One is the orange line and then is the gray line where which these are the EB limits and the full service brake limits. But now suddenly when certain brake force is developed along the length of the train, another curve is coming, that is a green curve, that is called as the estimate release speed. That is the speed which the train should attain such that I can definitely say that whatever air force available in the train is able to meet the target speed. That is the new algorithm, a new approach which I have introduced. So this is computed real time on the train. So even though the coaches are different or the wagons are different, we can have a boundary conditions. Suppose in the boxen, whatever PD sir told, boxen has a different kinds of wagons, boxen AL, boxen HL, boxen MS, boxen EL. So axle load is also varying from total load carrying capacity from 81 tons to 100 tons. So different deceleration constants are possible. So to ensure safety, we can take a minimum deceleration constant, but the real-time computation happens. The train is able to understand what is the deceleration achieved by the train and whether this deceleration coupled with the time taken to release the brake is sufficient enough to meet a target speed. If that is the target speed is there, then I am successfully or confidently release the brake such that my speed on the target is accurately equal to the target speed without loss of operation capacity. So this is the basic principle. So far whatever conventional algorithms we were using, they don't have this approach. So what we have done is we have added a additional real-time algorithm. One is once the information of target speed And once the information of gradient is available to the locomotive compute these curves, full service braking curve, emergency braking curve, well in advance. But what is real time? Once the brake is triggered, it starts monitoring the brake force available in the train. If the brake force generated is sufficient enough to meet the target speed, then I will clearly release the brake, even though if it is more than the full service braking limit. So this is the new concept which we have come up with, and we are testing excessively in the Western Railway Ahmedabad Baroda section. And this approach is called as release optimization. And additional features we have introduced for specifically to Indian conditions, which were not there in any global conventional approaches. Are Indian Railways, the drivers are able to handle variability in braking or variability in coaches or different countries, is that they will drive little conservatively. So we have a concept, suppose if your approaching signal is red, then if you want to pass a yellow signal at 50 kmph, 60 kmph. So these kind of things are not available in global technology, but we have given one flag. Suppose if you configure that virtual signal will become a target. Suppose if you want to cross every train yellow signal at 80 kmph, then you can enable this flag and make that distance programmed in the algorithm. Then it will monitor the supervision the movement of the train with reference to the virtual speed, that is 80 kmph between the yellow aspect to red aspect. So this kind of specific customization things also we have introduced. In addition to that, we can have a suppose most of the times in the operations, whenever LHB coach springs are broken or any damage, they will certify reduced speed on the BPC. So we can also configure that Locopilot can feed that reduced speed, so that the train supervision will happen with the reduced speed instead of the maximum permitted speed of the train. So some coasting region also we have introduced to ensure proper stopping at the train. But now we are getting away with this coasting region because our optimization is working reasonably beyond the satisfactory limits. That's why we are getting away with this coasting region. So this is the real example. So the right side curve is the negotiation of a 30 kmph loop line with a 20 LHB, 16 LHB rake formation in the Ahmedabad Baroda section. So when the brake was triggered, when there is no optimization, even though we have released the brakes around 35 kmph, the train continued to decelerate and stopped before the loop line. Whereas the bottom left side curve, if you see, the same similar initial conditions, we have applied a brake at 80 kmph, and we have released the brake around 65 or 62 kmph, and the train is able to negotiate properly on the point at a speed of 28 kmph. So there is no loss of operating efficiency, and moreover it is like optimizing braking towards real time or automatic driving of the train on the points. So that kind of approach we are working on. These are the different results which we have obtained in these trials. So different initial conditions, different locations, different weather conditions. Some of the cases we have even with heavy rains in the section also there, and different rolling stocks we have taken. We have taken 20 LHB car rake and 16 LHB car rake, and further we have loaded these 16 LHB cars with sandbags to simulate the load condition, and we have tested even with isolation of brake cylinders also to simulate the load. So under all these conditions, because of this optimization, the system is able to adjust accordingly to the requirement and able to stop within a band of 30 to 18 meters before the foot of the signal. And in 30 kmph loop line control, we are able to negotiate some experiments also there. We are able to negotiate within plus or minus 5 kmph, because mostly 32 to 25 kmph on the face of the point. So that is how our algorithm is able to perform in the field. This is one more thing. The capability of radio-based systems is most important. Conventionally, world over, we have ETCS level 1 and ETCS level 2. So this question has come when we want to prevent a SPAD. Actually, Kavach is capable of preventing the SPAD, which is not possible with the ETCS level 1 kind of spot kind of communications, where we have to give certain release speed such that the target or the train comes to the foot of the signal and then reads the aspect of the signal and able to decide whether to apply the brake or whether to continue. So that kind of requirement is not there because of the radio-based approach. And the radio-based approach, we are able to prevent the SPAD and also bring the locomotive or train very near to the foot of the signal. So this is the basic concept. So the spot and radio-based communication. In the spot communication, we have ballast based approach. The information related to signal aspect is available in the ballast, and as and when the train approaches the foot of the signal with some release speed, it reads the signal aspect through the ballast and try to decide whether to increase the movement authority or next to apply the brake. Whereas in the radio based communication, the locomotive or train already knows the aspect of the approaching signal due to the communication backbone, and it is able to decide whether to apply the brake, whether to release the brake. All these things are possible, and SPAD prevention is also possible. So these are the advantages of radio based communication. So if you see what is the type of information exchange, how this exchange happens in the non-radio based and radio based. In the radio based communication, the ability to stop before the signal is there. In non-radio based, that is not possible. Enhancement in safety also, because SPAD prevention is possible. So this is more radio based communication, and non-radio based is not very less. Line capacity, that is detrimental, whereas radio based communication enhances the line capacity. Design effort, radio based is multifold, whereas non-radio based is simple. Need for communication backbone, this is the most important aspect. So we need a communication backbone to have a radio based train control system, and this is also suitable for dense traffic networks. So at this juncture, the radio based communication ETCS is a GSM R technology, which is predominantly known as 2G. So when this Kavach was being developed in India, then we don't have any GSM R technology readily available for us, and then it is not prudent also at the time because 3G is coming, and moreover LTE was not at mature to a stage which can be deployable in India. So at that time, innovative radio communication backbone is possible, which has the capability to enhance safety and as well as operational flexibility. And this innovation solution has been developed by our innovative solution developed by our PED sir, who is the architect of Kavach also, who has developed this communication backbone, which is critical in the Kavach architecture to exchange of information between the locomotive and station, and also onboard Kavach to onboard Kavach. These are the two unique features which are pertaining to Indian Railways only, that new innovative communication backbone. And this customized solution also provides a high update rate as compared to 2G, and it is gainfully used for better train control. Now at this, I will request PD sir to continue further.
Coming, thank you. Before we conclude, just coming towards the conclusive slides, etc. See, what we had done, just one example. Sometimes you will find occasional glitches when you implement the logic. So at that time, we should not ignore that, and we should not compromise. So one such kind we were occasionally facing on account of implementation. Then we tried to capture it purposely and deliberately. This is just one sample use case. We tried to capture, and then we identified the cause and resolved that. Here you can see, because of you can say touching of that particular orange color and blue color. Blue color is current speed, and orange color is one of the threshold. So momentarily touching itself is causing sudden speed reduction by 10 kmph, which is unsolicited. So we captured, identified, resolved, and further tested. So this is the way we had done this particular testing of this particular thing, and whatever logics are devised. So activity will not be completed unless it is tested in the field. So we have got our technology partner also available in this hall, who facilitated us this particular testing. One of the Kavach OEMs, Mr. Manjunath, whether he is there in the hall. Yeah. May I request camera person to just, if possible, focus to, and a round of applause for Mr. Manjunath. Please get up. Polite request to you. So the braking algorithm developed by Center of Excellence and Mr. Nagaraj, we are working under his leadership and guidance for this project. So we could test with the help of the onboard Kavach provided by Gigitronics. Thank you very much. So I conclude here, and yeah, thank you very much.
Thanks, I think that was quite informative. In fact, that is the nearest, as I mentioned, we come to this topic as far as implementation on Indian Railway is concerned. Now we have Anushri Verma, ma'am. She's a senior director analyst, Gartner. Um, Ma'am is, as I mentioned, is a director analyst at Gartner, guiding C-suite leaders, CIOs, and IT leaders on digital strategy and technology adoption. She counsels both tech providers and end users on AI, Gen AI, agentic AI, and emerging tech, while also advising on policy and standards at government and industry forums. Ma'am shall be highlighting the transformative potential of generative AI and agentic AI, in essence, as to what makes AI agentic and how is it different from regular AI? What are the Gen AI and agentic AI use cases in production? How agentic AI moves beyond traditional automation by enabling dynamic context-aware processes that can adapt, learn, and optimize outcomes with minimal human intervention. Ma'am.
Thank you, sir, for that introduction. And thank you for inviting us here. It's amazing to see how far it has come in these 40 years. And we're discussing perception and intelligence and control today. Whereas my hometown just got a railway station a few years back. And and the wonderful presentations that were discussed today, from sense, think and act, to putting things into action, and other presentations, we are all talking about taking action and moving towards autonomous trains, like the Russian railways example, right? But as long as we have humans in the loop, do you think a target of achieving 95% on time arrivals or zero fatalities is possible as long as a human intervention is there in the systems? I'm not saying humans are out of jobs, but humans have to be there to govern them or be on the loop. But humans in the loop of these systems, as the Russian Railways also was mentioning, that we can monitor and have operators, but if we have to achieve autonomous operations, then we have to let systems run on their own, or have predictive systems manage the systems autonomously, right? And with the technical audience that we have here, we're going to discuss generative AI and agentic AI today, because these are the key technologies that are needed for autonomous trains. So we at Gartner, just a quick introduction. We have about 2,200 experts like me, and industry experts at Gartner who are focused on certain areas. I come from an emerging technologies practice, so I'm here to discuss the emerging technology around AI space. But other statistics I mentioned, I'm not going to delve deep on those because that's not the agenda for today. So we're going to discuss about AI, Gen AI, and agentic AI. What are the use cases that we're seeing across the world, except Russian railways, and the best practices for adopting AI, these AI practices in your systems. So when we discuss this issue with a number of different leaders across, so all the CEOs and senior business executives across the globe, everyone talked about entirely only AI. So they all want to be AI first organizations, not embed AI later into their systems. And when we're talking about agentic, generative AI, you hear all the hype, right? Every day in the newspaper, you read about agentic AI, what are the state of the art possible kind of use cases, right? But how much of that is possible and in production? Because we are also seeing some failures around agenting. So I don't want to overpromise that it is transformative, yes, but when applied in a correct fashion. And that's where Gartner experts come in to tell you the examples of where it is applied effectively in production. So AI is a combinatorial disruption. So don't waste time in separating out, what is generative AI, where can I use ML models, where can I use different kind of techniques. If it is going to be AI first, it is going to be either a combination of models also, because we've seen certain use cases in finance where we're talking about using over 100 models for financial compliance and reporting. So there are use cases as such, there are also accuracy problems and so on. So everything needs to be kept in consideration. So we do need to use a combination of AI practices. And therefore, there needs to be a strategic AI discipline for each of the mission critical priorities. So if we are trying to achieve 95% on-time arrivals, or we're trying to achieve zero fatalities, there needs to be a discipline for achieving that, not trying to implement force-fit emerging technologies. So when we, look at the overall emerging technology themes in India, so there are 5 broad categories. Of course, generative AI is there, and we talk about agentic AI also, and software developers, and all the technologies leading to software, open source, and everything that you know about. Security, that you don't need to think about it as an afterthought, but it has to be secure by design. Because if you're talking about autonomous operations, there needs to be security that is already embedded so that no one ultimately gets hold of that entire system. Cloud, obviously hosting the entire thing, and data and analytics to run this entire and host and get it ready as well. So when we look at all the technologies across these 5 broad themes, so these are the 5 broad themes around where India is focusing on the emerging technologies. Now, this is broken up by different emerging technologies, and this research obviously goes into more detail. This is only a graphic. I know there are a number of technologies mentioned here, but what we talk about is these concentric circles that you see here. One is the range. How fast is this technology moving towards the center? So accordingly, you invest in that technology. So if you look at agentic AI, right, on the left-hand side with a diamond shape orange star, that's outside. So we are still going to take around 6 to 8 years to reach the mainstream adoption of agentic AI. Now, we'll talk about what is agentic, what are AI agents and all of that. But broadly giving you the picture, for example, Gen AI enabled virtual assistants, all the chatbots, all, everything around that you see, it's almost there in the market as a mainstream product today. That's why it's towards the center. There are other technologies also that are very much needed for building these systems. So for example, if there is a signaling, or there are certain aspects that you need to implement for agentic, you will need vector databases, knowledge graphs, AI ready data. So everything around the data and analytics practice becomes very important to ultimately develop that kind of a system and use it. Then we have around cloud and security, where we're talking about EDA, SASE, threat exposure management, identity threat detection and response, and so on. So there are different technologies, and the mass indicates how transformative is that technology. So agentic AI is transformative, right? Because we are talking about it being implemented across different industries. But then again, I'm still cautioning you against misapplication. But then there are technologies that don't have that high mass. There are technologies that just, for example, vector databases on the left-hand side bottom, you see there as a square that has a medium mass. It means it is important, but it doesn't have a transformative potential. It has an incremental benefit when you implement vector databases. So this is used to understand when to invest and how much to invest in that particular technology, and what are the use cases for each of these technologies. But broadly, these are the themes and technologies that we see emerging in India today. And you'll also see multilingual LLMs there. So because again, India is becoming the epicenter for having these multilingual language models for all the systems. Now, but with all these technologies that we see, Gen AI and agentic AI, I see the smile on everyone's face, is leading the pack. When we take in discussions over, Gartner takes in around more than 4 lakh discussions every year. We're talking about Gen AI and agentic AI, completely, because everyone wants to know about that. We're talking about, there is a hype as well. I'm not saying everything is in production. There are still POCs that are happening, and all the large vendors are showcasing their POCs as the use case that you should be adopting. So you have to also understand that where is the hype, because it is at the peak of the hype cycle, but then there are other technologies also that are needed for achieving that kind of an outcome. And when we talk about transportation specifically to the CIOs for transportation, what technologies are they deploying at this point in time? It is AI, Gen AI, and low-code, no-code development platforms. Now, in various use cases, I see some heads nodding because in various use cases, we do know that low-code, no-code becomes very useful, right? Because it can be easily integrated, but it cannot be customized. So there are challenges and there are outcomes that you can achieve easily. But so you do need to weigh on if you need a pro code kind of an application platform, or do you need a low code, no code kind of a use case to be implemented. So there are, but then we do see a lot of, because of agentic AI, hype, I would say, low code, no code is being used a lot, and they are, really being implemented because of its ease of implementation. But then you need to understand those are pre-built agents and not customizable agents to your platform. So when we talk about generative AI, we're just going to talk about a little bit of the definition so that it's clear for everyone that what is, we're talking about AI agents, machine learning, or agentic here, focusing today on a generative AI and agentic. Generative AI is meant to generate things, whether it is a Shah Rukh Khan's ad, or whether we're talking about a content collateral, marketing collateral, anything around generation of content, audio, image, video is generative AI, and you're using all these chat GPTs, everything around generation. Even chat GPT is an example of a generative AI kind of a technology. But when we talk about AI agents and agentic AI, the chat GPT is not an AI agent. It's not an agentic AI kind of a application also, because many people are, because agentic AI has come after generative AI, we're talking about it being an advancement of generative AI. It is not. It is not an advancement of generative AI. It is meant to take actions. If you see that highlighted, it is meant to take action. Now, sending an FAQ document or sending a summarization is not an action, because that agentic is not, you're not actually achieving the outcome. You're just over investing in that and trying to provide some context to that kind of a summary. It's a simple generative AI case. You're still just integrating a language model. Now you don't even need to use a large language model. I know, because of being open source and being easily available and being pushed by a lot of larger vendors, you may need to integrate a large language model in many use cases that you see, and it's easily available as well. So you're seeing that. But if you need to control the investments, you can easily go ahead for a smaller language model or a domain specific model, which a few of the speakers also mentioned to you, right? That you can focus on just domain specific models to your particular area, because then you're not spending so much on fine tuning, because getting the data AI ready is a huge investment, which generally is not discussed at the start. Now, when we talk about agentic AI and AI agents, now you may have heard both these words, right? And both of them are used interchangeably today across everything that I read on different media channels. They are all using very much different or interchangeable definitions and so on. But when we talk about an AI practice that is being leveraged to take actions, that is agentic AI. But the software entity that is taking action, or the head of the agentic AI workflow, the design pattern that you develop, the head, it can be a virtual assistant, it may not be a virtual assistant, that is an AI agent. So AI agent is taking an action, yes, but it is taking an action based on an AI practice that is agentic AI. So if tomorrow or today evening, if someone again comes up to you that this is an advanced AI agent, you do need to understand if it is leveraging an agentic AI practice. And not all use cases that we see today are leveraging agentic AI practice. And I'll show you that in some time as well. So beware of AI agent washing, because there are many vendors who are actually, and you'll see it across several places, that everyone is calling themselves, repackage their products and selling them as a finance agent, an HR agent. This is a recruiter agent. This is a some kind of a operator agent. But you have to understand where are you investing in those kind of emerging technologies, and not just fall for the hype of it. So generative AI is meant to augment, because it is meant to help you with the processes by creating certain or generating certain artifacts, right? But when we're talking about agentic, it is meant to automate. So the humans are free from that kind of a task. So the ultimate potential of agentic AI is transformative, yes. But because today we are implementing just simple AI agents as chatbots or some those kind of use cases, you don't see the transformative potential. But if you can, for example, any kind of signal monitoring, any kind of use cases that can be completely automated in the future, slowly you move from semi-autonomous to fully autonomous, you start talking about automating that process completely and not have humans in the loop at all. And that's when you achieve the transformative potential of agent, because that's the ideal kind of a flow chart for using agentic AI into your use cases. So we do expect that in the next year, you'll see a lot of POCs not going into production. You'll see a lot of agentic AI projects getting cancelled because right now it is at a peak of its hype, and it's being used everywhere, and there is a lot of agent washing that is being done in all the products. So just incrementally updating an application because it has an agent interface. So you have to also look at if your if your vision is to improve the employee experience, then it is fine. But if you're going to use agentic AI as an emerging technology and use that potential, then you have to look at processes that can be automated through agentic AI, and humans are not even involved in it ultimately in the longer period of time. So it has a self-learning loop. So there are various technologies that you need to integrate when implementing agentic there. So we define the entire agentic AI journey as a spectrum. Now, AI agency that you've seen a lot of research papers, I understand that most of you are technical here, and you may have seen some academic research and everything that talks about AI agency. So AI agency is the kind of capability that each agent has. All the chatbots, all the virtual assistant, all the, we have even for, any kind of application, whether it is media or whether it is booking systems or it is a travel app, those are deterministic chatbots. They are scripted, they react, the blue one that you see here, on the left hand side. They are scripted, they react when you ask them for a response. They have a certain frame in which they work. They can't work outside that kind of a framework. They have, they don't have any AI agency in summary that we say. They have zero levels of AI agency. And what you see in the market today is, let me integrate an LLM, and this AI assistant will write an email for you. This AI assistant will do some kind of a task, calendar management, and appointment will be scheduled, the tickets will be booked. Those are LLM based AI assistants that you see in the market, and they do advance some level of agency a little bit, but most of the products are today in the market or on the left hand side of the spectrum. They don't have any proactive planning, achieve any any complex goals. So ultimately we are still on the left hand side from a maturity standpoint, and it is not, we don't have any products that achieve a high level of AI agency there. And if you see the market today from a landscape point of view, there are options obviously to buy towards a build scenario. So you have pre-built agents that are available, very task specific agents for any kind of automated billing or any kind of agents that are very specific for a particular task. And most of the market, I would say honestly, which I speak to the CIOs, are limited to the pre-built agents. They want to quickly integrate something, so let me use pre-built agents and quickly integrate something because I can show to my board as well that there has been something implemented. Now, we also have low-code, no-code agent builders, as I was explaining to you in the initial slides. Low-code, no-code agent builders are also used in certain use cases. And as you go towards the right, it is more towards building your own platforms, using vendors like AutoGen by Microsoft, or using Crew AI and LangGraph and so on, using them to build a multi-agent kind of a system, and simulation platforms where you simulate the kind of behavior that you would want the agent to perform. So there are simulation platforms as well. So if you look at some of the sample vendors, again, it's not an exhaustive set because otherwise we'll have more than 1,000 vendors here. some of the pre-built agents that are available, a mix of companies from India and a global, and some low-code, no-code agents, some code-based like LangGraph Crew AI that I was talking to you about, and some who allow you to code and train the agents on their platform as well, and some who are actually offering, again, even Microsoft, Salesforce, all these AWS that you hear, are all offering agents, right from pre-built agents to some builder platforms where you can build like AWS Bedrock agent, or we have Microsoft's OpenAI platform, right, where you can build agents. So they're offering right from pre-built agents to building agents on your own. So this is the broadly the landscape when we talk about agentic AI. Now coming to what use cases are we, can we or are we seeing in production today in the current scenario? At Gartner, we would not like to fall in for the hype and look at just POCs and state of the art kind of possible use cases. We would want to see what is actually happening on the ground. And honestly, there are very limited use cases. More than 90% are still in POCs, and very few are in production. And when we talk about in production, most of them are utilizing conversational assistants, just incrementally upgrading the application to an AI agent-based interface. So enhancing your interaction with that application, and or the other side of the things. And some of the advanced companies have done it. I'll show you one or two use cases there also, but very limited in this sector, where we're trying to automate processes through agentic AI kind of implementations. Now, in various use cases, as I was telling you, and I put an AI, Gen AI, agentic AI in purpose, because I don't think that even agentic AI itself can be used without other practices. There has to be multiple models that need to be used. There needs to be machine learning. For example, if you're just talking about passenger experience, sorry, which is contactless in many countries that we see in terms of implementation, AI agents can be used, right? And you can make it variable from a passenger experience, or we're talking about predictive maintenance, enhanced capacity utilization, or operational efficiency. There can be a combination of AI practices that are used, and not necessarily agentic AI is implemented in all of these kind of use cases. So one of the use cases which we see with Dushban, where they're using, and I heard one of the speakers also talking about reinforcement learning. So multi-agent reinforcement learning, where every train becomes its own decision-making unit. And if you, again, we don't have the technical architecture here, but what they're trying to do is that whenever there is a disruption, there is immediately there is a new schedule that is within seconds. If you see, the system creates a new schedule for dozens of trains, and not just ones that are directly impacted by that kind of a disruption, but for other trains that will be indirectly changed because of the disruption in that kind of a route. So we do see that, and there is there is an interview also around Dushban using multi-agent reinforcement learning, if you look on search. So they also use obviously the voice response system. Again, I'm not saying that it's a very advanced use case, but multilingual, scalable, and learning AI kind of concierge solutions that is being used. There are avatars that are used, there are digital humans that are used in such scenario, and it's a smart interactive voice response system. SNCF, which again uses, as I was telling you, digital twins, and I've started seeing use cases where they're using digital twins and also using agents layered on top of that to take actions, because digital twins are already giving you that kind of a data that can be used for AI agents to be used on top of that as a layer. So SNCF is leveraging that to have 100% on-time preventive maintenance and downtime and reduction in energy consumption and so on. So they have that target. So it's not just about improving productivity or so on, but it's about improving accuracy with these AI models. And if you achieve accuracy, then it translates into all the goals in terms of achieving zero fatality, or achieving a 95% on time arrival and so on. There is another one around domain expert AI agents for industrial applications, where there was a resource crunch because the experienced engineers were mostly nearing retirement, and how they implemented domain expert agents to take up that task. So they reduced the cost by 10%, and in fact saved time as well, around 1,000 hours for that company of AI automating. So these are use cases that could be shared. Obviously, we can't share some use cases which are under NDA with us. So until it becomes public or there is an approval with the vendor. Now, the best practices that we would suggest around adopting AI, and these are just some examples that are already in production, right? I'm not showing you anything that is possible. Obviously, maybe Indian Railways is the first one to do something like that. But the best practices that we talk about how to do that for implementing agentic, if we do not need AI for decision making in any kind of a use case, I would not recommend to use agentic or any kind of AI implementation or generative AI in that kind of a thing. If it's a simple scripted workflow, you do not need to invest more in that kind of a thing. It's a simple deterministic automation. An RPA vendor can do that, or any kind of other practices can do that. You do not need to look at these techniques, because these techniques, when you scale it up, becomes costly, because you're going to use multiple models, you're going to use security layering techniques, you're going to use techniques that you need to host it on the cloud, get the data ready, get it how to govern those AI agents. As of now, the maturity of this technology is not there that we talk about how to govern these AI agents, right? Every vendor will show you the result or the outcome that can be achieved through these AI agents, but they can't, a third party can't show you the outcome that the other party of AI agents is achieving. So there are, there's a flowchart that you can see here, and some use cases where agentic AI is not required at all, which I was mentioning at the start. And you can simply integrate a smaller language model or anything that your obviously it depends on the use case. Like for ticket generation, IT ticket generation we're talking about, not railway ticket generation, or any recommendations. But then there are agentic AI where it is already in production, and healthcare is actually leading this technology in terms of in production kind of use cases. And the last part of it, where we talk about this best step practices, because every use case doesn't need generative AI, agentic AI, and everything that is hyped, right? You do need to look at your outcome, analyze the approach, look at the platforms that you need to use, mitigate the risk, and standardize and execute it. Again, there are details within each, but for this session, I'll keep it limited here. So thank you.
Thank you, ma'am. Thanks for highlighting the subtleties of differences between AI, Gen AI, genetic or generative AI, and AI agents, and more importantly, putting the perspective as to AI not for the sake of AI. I mean, looking at what is exactly required based on the use cases and operational efficiency, safety, decide on the outcome, and then decide as to what tool you use. I think that was a great takeaway. Now, I think we come to the end of the session. I would request Sumit Garg to just make a summarized presentation of the entire proceedings, not more than a minute. And um, yeah, and just before that, I think we can have some Q&A, because it's time for lunch, but I think you can also converse with the speakers during the lunch. But yeah, maybe a couple. Samir, you can talk. I can